In the autumn of 1967, a graduate student at Cambridge was working her way through hundreds of feet of paper chart looking for a particular kind of cosmic signal. She had spent 2 years helping to build the strange telescope that produced the charts, a field full of wooden posts and wire, more like a hop garden than an observatory. And one day, on one small stretch of paper, she found something that did not belong. A bit of scruff, she called it. A signal too regular, too precise, too rhythmic to match anything astronomers knew. For a brief period before anyone understood what it was, there was a real possibility on the table, a possibility taken seriously enough to be discussed in hushed tones. The signal was so perfectly regular that it looked artificial. It looked like it might be a beacon sent by another civilization somewhere out among the stars. The team gave it a half-joking name that captured the thought they could not quite dismiss: Little Green Men. Tonight we'll move slowly through the whole story. What the signal actually was, why it briefly looked like a message from another world, how the truth turned out to be even stranger than aliens, and what the episode taught us about how science meets the unknown. If this kind of slow, careful exploration is what you came for, consider hitting like and subscribing. It helps more than you might think. Now, let's begin. By the middle of the 20th century, astronomers had grown comfortable with a certain picture of the heavens. The sky had been studied for thousands of years, mapped in ever greater detail, catalogued and classified. Stars were understood, at least in broad outline, balls of gas, fusing hydrogen in their cores, shining steadily for billions of years. Galaxies had been recognized as vast collections of stars far beyond our own. The universe seemed, if not fully understood, at least reasonably well charted. The major categories of objects were known. What remained, many thought, was to fill in the details. This sense of a largely mapped sky was reinforced by the kind of light astronomers had been able to study. For most of history, astronomy had been done with visible light, the light the human eye can see, gathered by telescopes and later recorded on photographic plates. Visible light had revealed a great deal: the stars, the planets, the nebulae, the galaxies. It had built up the comfortable picture of a well-understood cosmos. But visible light is only a narrow band of the full electromagnetic spectrum, and there were other kinds of light that astronomers had barely begun to explore. Radio waves are one such kind. They are light in the same sense that visible light is light, electromagnetic radiation, but with much longer wavelengths far beyond what the eye can detect. For most of history, no one knew that objects in space emitted radio waves, because no one had the instruments to detect them. The radio sky was completely invisible, an entire dimension of the cosmos hidden from view. It was only in the 20th century that this began to change, and the change would prove to be revolutionary. The first hint came in the 1930s, when an engineer named Karl Jansky, investigating sources of radio static for a telephone company, found that some of the static came from the sky, specifically from the direction of the centre of our galaxy. This was the first detection of cosmic radio waves, the first sign that the universe was emitting radiation in this invisible band. It was a remarkable discovery, but its significance was not immediately appreciated. Radio astronomy as a field developed slowly at first. After the Second World War, radio astronomy began to grow rapidly. The war had driven major advances in radio technology, developed for radar, and these advances could now be turned toward the sky. Astronomers built radio telescopes, instruments designed to detect and study cosmic radio waves, and began to explore the radio sky in earnest. What they found was a universe far more active and varied than the visible light view had suggested. The radio sky was full of surprises. Among the surprises were objects that emitted enormous amounts of radio energy, far more than ordinary stars. Some of these were eventually identified as distant galaxies with violently active cores. Others were more mysterious. In the early 1960s, astronomers identified a class of objects that appeared star-like but emitted strange radio signals, and were eventually found to be extraordinarily distant and luminous. These came to be called quasars, and they were among the most exciting and puzzling objects revealed by radio astronomy. Understanding them was a major goal of the field. It was the study of quasars, in fact, that would lead somewhat indirectly to the discovery at the heart of this story. To study quasars, astronomers needed to understand a phenomenon called scintillation, a kind of twinkling of radio sources caused by the solar wind that could be used to identify and study compact radio objects like quasars. A telescope designed to detect this scintillation would need to be sensitive to rapid variations in radio signals, and it was exactly such a telescope, built for exactly this purpose, that would detect something no one was looking for. The sky, in other words, was not as fully mapped as it seemed. The comfortable picture, built on visible light, was about to be disrupted by what the radio sky would reveal. The universe held categories of objects that no one had imagined, objects so strange that when their signals were first detected, the possibility of alien intelligence seemed almost reasonable. The mapped sky was about to acquire a new and startling feature, one that would change astronomy and reveal a kind of object stranger than anything in the existing catalogues. The instrument that would reveal it was already being built, in a muddy field outside Cambridge, by a team that had no idea what they were about to find. They were looking for quasars. They would ultimately find something far stranger, and for a brief electric moment, they would wonder whether they had found someone rather than something. The telescope that would make the discovery did not look like most people's image of a telescope. There was no great dish, no gleaming instrument pointed at the sky. Instead, there was a field, a large field in the Cambridgeshire countryside, filled with rows of wooden posts strung with wire. To an untrained eye, it might have looked like a hop garden or some strange agricultural installation, rather than a scientific instrument. But this array of posts and wire was a radio telescope designed to detect the faint radio signals that astronomers wanted to study. The telescope was built by a research group at Cambridge led by Anthony Hewish, who was interested in studying quasars through the scintillation technique. The instrument was designed to be sensitive to rapid fluctuations in radio signals at a particular frequency, fluctuations caused by the solar wind passing in front of compact radio sources. To detect these fluctuations, the telescope needed to cover a large area, to collect enough of the faint radio signals, and it needed to respond quickly to capture rapid variations. The array of posts and wire spread across a large field met these requirements. The scale of the instrument was considerable. The array covered an area of about 4.5 acres, roughly the size of several football fields. It consisted of more than 1,000 wooden posts supporting a network of wire antennas. The total length of wire ran to many miles. Building it was a major undertaking, requiring a great deal of physical labour. The posts had to be set in the ground, the wire strung between them, the connections made. It was not delicate work. It involved sledgehammers and soldering, digging and stringing carried out over a period of about 2 years. Much of this labour was performed by the graduate students in the research group, including a young woman named Jocelyn Bell, who would later become Jocelyn Bell Burnell. She spent 2 years helping to construct the telescope, working in the field, setting posts and stringing wire alongside the others. This was not glamorous or rigorous work, but it was essential and it gave her an intimate familiarity with the instrument, a familiarity that would prove important when the telescope began to produce data. She knew the telescope from the ground up, having helped to build it with her own hands. The telescope operated at a radio frequency of about 81 MHz, chosen for its sensitivity to the scintillation effect being studied. As the Earth rotated, the telescope swept across the sky, detecting radio sources as they passed overhead. The signals it detected were recorded, not digitally as would be done today, but on paper charts drawn by pens that traced the strength of the radio signal over time. The telescope produced these charts continuously, generating a vast amount of paper that had to be examined by hand. The use of paper charts is worth dwelling on because it shaped how the discovery was made. There were no computers analysing the data automatically, flagging interesting signals. Instead, the charts had to be read by a human being, looking at the wiggling lines traced by the pens and interpreting what they meant. This was painstaking work, requiring patience, attention, and skill. The reader had to distinguish real cosmic signals from the various sources of interference, radio transmissions from Earth, electrical noise, and other spurious effects that could also mark the charts. The telescope went into operation in 1967 after its long construction. It began producing its charts, sweeping the sky, recording the radio signals it detected. The data poured out, foot after foot of paper day after day. Someone had to read it all to find the quasars and other compact radio sources the telescope was built to study. That someone, primarily, was Jocelyn Bell. It was her job to operate the telescope and to analyse the charts it produced, to turn the wiggling lines into scientific understanding. This humble instrument, posts and wire in a field and charts traced by pens, was about to make one of the most significant discoveries in the history of astronomy. It is a reminder that great discoveries do not always come from the most impressive instruments. They come from the right instrument, used carefully by someone paying attention. The telescope of wire and wooden posts was the right instrument, and Jocelyn Bell was the someone. Together, they were about to reveal something the universe had been hiding, and it is worth noting that the instrument was not even designed to find what it found. It was built to study quasars through the scintillation technique. The discovery of pulsars was, in this sense, a byproduct, an accident of an instrument sensitive enough and an observer attentive enough to catch something no one was looking for. Jocelyn Bell was born in 1943 in Northern Ireland. Her interest in astronomy began early, sparked in part by books from the local library, including a book on astronomy by Fred Hoyle that she read at the age of 14, and that, by her own account, hooked her on the subject. She grew up near the Armagh Observatory, whose staff encouraged her interest. Her parents believed strongly in education for women, which was not universal at the time, and supported her pursuit of science. These early influences set her on the path toward astronomy. Her education was not without obstacles. At one point, she failed an examination that was required for students wishing to pursue higher education and was sent to a boarding school to continue her studies. She persevered, eventually earning a degree in physics from the University of Glasgow in 1965. In that program, she was often the only woman in her classes, which subjected her to various forms of discrimination and harassment that were common for women in science at the time. She endured these difficulties and completed her degree, then went on to Cambridge to pursue a doctorate. At Cambridge, she joined the research group led by Anthony Hewish, working on the radio telescope being built to study quasars. As a graduate student, her role included the physical labour of building the telescope and then the analytical labour of reading its charts. This was the ordinary work of a doctoral student in radio astronomy at the time, demanding, detailed, often tedious, but essential to the research. She threw herself into it, developing a deep familiarity with the instrument and its data. When the telescope went into operation in 1967, Bell took on the task of analysing the charts it produced. The telescope generated about 100 feet of paper chart every few days, and it was her responsibility to examine all of it, identifying the radio sources and distinguishing real signals from interference. This required reading the charts carefully, recognising the characteristic patterns of different kinds of signals, and noting anything unusual. It was a job that demanded sustained attention and a good eye for patterns. Bell proved to be exceptionally good at this work. Reading the charts was not a mechanical task. It required judgment and skill. The signals were often faint and the interference could be confusing. Distinguishing a real cosmic source from a spurious one took experience and care. Bell developed a feel for the data, an ability to recognise the various kinds of signals and to spot anything that did not fit. This skill would prove crucial. The discovery she was about to make depended on her ability to notice something subtle, something that a less attentive or less skilled observer might have missed or dismissed. It is worth emphasising the human element here. The discovery was not made by an automated system or a sophisticated algorithm. It was made by a person, reading charts by hand, who noticed something unusual and had the curiosity and persistence to investigate it. This kind of discovery, depending on human attention and judgment, was characteristic of the era, before computers took over much of the work of data analysis. The story of the discovery is, in large part, the story of a person paying close attention to her data and refusing to ignore something that did not make sense. Bell's familiarity with the telescope and its data gave her a particular advantage. Because she had helped to build the instrument, she understood its quirks and characteristics. Because she had read so much of its output, she knew what normal signals looked like. This deep knowledge meant that when something abnormal appeared, she was well positioned to recognize it as genuinely abnormal, not just an artifact or a familiar kind of interference, but something new. Her preparation, in other words, made her ready to notice the unexpected when it appeared, and the unexpected did appear. Amid the ordinary signals and interference, on one stretch of chart, there was something that Bell could not immediately explain. It was small, taking up only a tiny fraction of the chart, but it was distinctive. It did not match the quasars she was looking for, nor the familiar kinds of interference. It was, in her own description, a bit of scruff, and her attention to that small anomalous mark would lead to one of the great discoveries of 20th century astronomy. The graduate student who watched the charts was about to find something no one had ever seen. That she was the one to find it was no accident. Her years of building the telescope, her months of reading its charts, her trained eye and stubborn curiosity, all of it had prepared her for exactly this moment, even though neither she nor anyone else knew it. To appreciate the discovery, it helps to understand the sheer volume of data that Bell had to analyze. The telescope produced paper charts continuously. As the pens traced the strength of the radio signals over time, the amount of paper was enormous. Over the course of its operation, the telescope generated charts at a rate that required Bell to analyze about 100 feet of paper every few days, and across the full survey, miles of chart in total. Every inch of it had to be examined by eye. This was a formidable task. Reading 100 feet of chart meant looking at a continuous record of the radio signals, tracing the wiggling lines, and interpreting what they represented. Most of the chart showed ordinary signals or noise, the background hum of the radio sky, punctuated by the occasional radio source or burst of interference. The interesting signals, the quasars and other compact sources the telescope was built to find, appeared as particular patterns amid the general noise. Finding them required scanning the entire length of chart, attentive to the patterns that mattered. The work was repetitive and demanding. Day after day, Bell examined the charts, looking for the signals of interest. It would have been easy to become careless, to let attention slip, to miss the subtle features amid the monotony. But the discovery depended precisely on not missing them. The anomalous signal that Bell found was small, dim-sats. It occupied only about a quarter inch of the chart out of the miles she analysed. Finding it required examining the charts with sustained care, not glossing over the small features. The scale of the task makes the discovery more impressive. Bell was not looking for the anomalous signal, she was looking for quasars. The anomaly appeared incidentally, a small mark amid the vast expanse of chart. To notice it, to recognise it as something unusual, and to remember having seen it before, required a remarkable level of attention to the data. A less careful analyst might have skimmed past it, dismissing it as noise or interference. Bell did not. She noticed it and she remembered it, and that made all the difference. The use of paper charts rather than automated data analysis was crucial to how the discovery unfolded. Today, such a survey would be analysed by computer, with algorithms searching for signals of interest. The anomalous signal might be flagged automatically, or it might be filtered out as noise depending on how the algorithms were designed. In 1967, the analysis depended on human judgment. Bell's eye, trained by long experience, caught what an algorithm might have missed, or might have flagged in a way that no one would have followed up. The human element was essential. There is a broader point here about the nature of scientific discovery. The discovery of pulsars was not the result of a deliberate search for pulsars. No one knew they existed. It was the result of careful attention to data gathered for another purpose. The anomalous signal appeared unexpectedly, and it was recognized as significant only because someone was paying close enough attention to notice it and curious enough to investigate it. Many discoveries happen this way, not through targeted searches, but through alert attention to the unexpected, encountered in the course of other work. Bell's diligence in analysing the charts reflected a particular scientific virtue, the willingness to take the data seriously, to examine it carefully, and to follow up on anomalies rather than dismissing them. This virtue is not glamorous. It involves long hours of careful, often tedious work. But it is essential to discovery. The universe reveals its secrets to those who pay attention, who notice the small anomalies and pursue them. Bell paid attention, and the universe rewarded her with one of the great discoveries of the century. It would have been so easy to do otherwise. A tired analyst near the end of a long day, glancing over yet another foot of chart, might have let the quarter-inch of scruff slide by unremarked. The discovery hung on the thin thread of one person's refusal to look away. So the volume of paper, the miles of chart, the daily grind of analysis, these were the setting for the discovery. Amid this vast flow of data, a small anomaly appeared, and a careful analyst noticed it. The discovery of pulsars began not with a dramatic moment of revelation, but with the patient, attentive work of reading charts, day after day, and refusing to ignore the bit of scruff that did not belong. It was a triumph of diligence as much as of insight. There is a quiet heroism in this kind of work, unglamorous, unrewarded in the moment, invisible to anyone watching. No one cheers for the analyst bent over a chart at the end of a long week. Yet it is exactly here, in the patient sifting of ordinary data, that the extraordinary is sometimes found. The anomaly first appeared as something Bell would later describe as bit of scruff, an irregular mark on the chart that did not match the pattern she was used to seeing. It was not the smooth signal of a quasar, nor the familiar forms of interference. It was something different, something that caught her attention precisely because it did not fit any of the expected categories. It was small and easy to overlook, but it was distinctive enough that Bell noticed it and registered it as unusual. What made the scruff particularly intriguing was that Bell had a nagging sense of having seen it before. As she continued analysing the charts, her memory began to prompt her, a feeling that this strange mark had appeared previously, from the same part of the sky. This sense of familiarity was important. A single anomalous mark might be dismissed as a one-time glitch, a random burst of interference, but a mark that recurred, that appeared repeatedly from the same location, was harder to dismiss. It suggested a persistent source, something real in the sky. Bell acted on her suspicion. She went back through earlier charts, looking for previous appearances of the scruff, and she found them. The strange mark had indeed appeared before, from the same position in the sky. This was significant. The signal was not a one-time event, but a recurring phenomenon tied to a particular location among the stars. As the Earth rotated and the telescope swept across the sky, the signal appeared whenever that particular part of the sky came into view. It was keeping its place among the stars, as Bell put it, behaving like a genuine celestial object. This recurrence was the first clue that the signal was real and astronomical, rather than spurious interference. Interference from Earth, radio transmissions, electrical noise, would not generally keep a fixed position among the stars. It would appear at various times and from various directions, tied to terrestrial sources rather than celestial ones. A signal that consistently appeared from the same point in the sky, rising and setting with the stars, was behaving like something out in space. The fixed celestial position pointed toward a genuine cosmic source. But if it was a cosmic source, it was a strange one. The signal did not match the quasars Bell was looking for, nor any other known type of astronomical object. It had characteristics that set it apart, that made it puzzling. The nature of those characteristics, which Bell would investigate further, was what made the signal so intriguing and eventually so startling. The bit of scruff was not just an anomaly, it was a sign of something genuinely new, a kind of object that had never been catalogued. Bell brought the anomaly to the attention of her supervisor, Anthony Hewish. His initial reaction was skepticism. Anomalous signals were common in radio astronomy, usually turning out to be interference or instrumental artifacts. Hewish's first thought was that the scruff was probably some form of interference, a spurious signal of terrestrial origin, not a genuine cosmic source. This skepticism was reasonable. Most anomalies do turn out to be mundane, but Bell's careful observation that the signal kept a fixed celestial position was hard to reconcile with simple interference, and it justified further investigation. The investigation would require better data. The signal had appeared on the ordinary charts, but those charts did not have enough time resolution to reveal its detailed structure. To understand what the signal really was, Bell and Hewish needed to observe it with a faster recording, one that could capture its behaviour in finer detail. This would require catching the signal again, when the relevant part of the sky was overhead, with the faster equipment running. It was not a trivial task, as the signal was intermittent and did not always appear, but it was the necessary next step. So the bit of scruff, the small mark that did not belong, set in motion a process of investigation. Bell had noticed it, recognised it as unusual, confirmed that it recurred from a fixed celestial position, and brought it to her supervisor. The next step was to observe it in greater detail, to find out what kind of signal it really was. That detailed observation would reveal something astonishing, a signal so regular, so precise, that it would raise, however briefly, the possibility of an intelligent origin. The scruff was about to become one of the most famous signals in the history of astronomy. What had begun as an irregular smudge, easily mistaken for noise, was on its way to becoming a landmark in the human understanding of the cosmos. The smallest of anomalies was about to open onto one of the largest of questions. When Bell and Hewish finally managed to observe the signal with a faster recording, capturing its detailed structure, they found something remarkable. The signal was not a continuous emission, nor a random fluctuation. It was a series of pulses, sharp, regular bursts of radio energy repeating with extraordinary precision. The pulses came about 1 1/3 seconds apart, one after another, with a regularity that was almost unbelievable. It was like a cosmic metronome, ticking away in the depths of space. The regularity was the most striking feature. Astronomical sources, in general, do not produce signals of such clockwork precision. The cosmos is a chaotic, turbulent place, and most cosmic signals reflect this. They vary irregularly, fluctuating in ways that reflect the messy physics of their sources. A signal that pulsed with the precision of a clock was unlike anything astronomers had seen. It seemed too regular to be natural, too precise to come from the ordinary chaotic processes of the universe. This precision is what made the signal so puzzling and so suggestive. On Earth, regular, precise signals are characteristic of artificial sources, machines, clocks, transmitters designed by intelligence to produce regular outputs. Natural processes, by contrast, tend to be irregular. The very regularity of the pulsing signal pointed, by analogy with terrestrial experience, toward an artificial origin. If a signal this regular had been detected on Earth, one would naturally assume it came from a machine. Finding it in space raised the unsettling question of what kind of machine, or what kind of source, could produce it. The period of the pulses, about 1.3 seconds, was itself significant. It was short, much shorter than the timescales associated with most astronomical phenomena, and it was extremely stable, maintaining its precise value pulse after pulse. The combination of a short period and high stability was difficult to explain with known astronomical sources. What kind of object could produce pulses this rapid and this regular? The known categories of astronomical objects did not seem to fit. The signal was genuinely anomalous, resisting explanation in terms of established astronomy. Bell and Hewish considered the possibility of interference, but the signal's behavior argued against it. The signal kept its fixed position among the stars, rising and setting with the celestial sphere, which pointed to a cosmic rather than terrestrial origin. Terrestrial interference would not generally behave this way. Moreover, the signal's characteristics, the sharp regular pulses, did not match known forms of interference. The more they investigated, the more it seemed that the signal was genuinely astronomical, genuinely coming from out in space, and genuinely unlike anything known. There was also the matter of the signal's frequency characteristics. The pulses appeared at a specific radio frequency, in a relatively narrow band rather than spread across a wide range of frequencies. This too was suggestive. Many natural cosmic sources emit across a broad range of frequencies, reflecting the broadband nature of the physical processes that produce the radiation. A signal concentrated in a narrow frequency band was, again, more reminiscent of an artificial transmitter, which would broadcast at a particular frequency, than of a broadband natural source. This added to the sense that the signal might be artificial. As the evidence accumulated, Bell and Hewish faced a genuinely puzzling situation. They had a signal that was clearly astronomical, fixed among the stars, but that had characteristics suggestive of an artificial source. Extreme regularity, a short stable period, a narrow frequency band. These characteristics did not fit any known natural astronomical object. The signal seemed to demand either a new kind of natural object, unlike anything previously known, or an artificial source, which, given its cosmic location, would mean an extraterrestrial intelligence. Neither possibility was comfortable, but one of them had to be true. It was this situation, a signal too regular to be natural yet clearly coming from space, that led to the famous, half-joking designation that the signal received. Unable to explain it by known natural process, and confronted with its eerily artificial regularity, the team gave it a name that acknowledged, however playfully, the possibility they could not quite rule out. The signal might, just might, be a message from another civilization. And so it was labelled with a name that has become legendary in the history of astronomy, Little Green Men. It is worth pausing on how genuinely strange the situation was. Here was a signal that behaved, in every measurable way, like a celestial object, rising and setting with the stars fixed in its place among them, and yet it carried the unmistakable fingerprint of regularity that, on Earth, only machines produce. The team was caught between two categories that had never before collided: the natural and the artificial, the cosmic and the engineered. The signal seemed to belong to both worlds and neither. This was the discomfort at the heart of the discovery, a phenomenon that astronomy's existing framework simply had no place for. Something would have to give. Either astronomy would admit a new kind of natural object, or something even more momentous. For a few weeks no one knew which. Before entertaining anything as extraordinary as an alien signal, Bell and Hewish had to rule out the ordinary explanations. This is a fundamental principle of science. Before accepting an extraordinary hypothesis, one must exhaust the mundane possibilities. An anomalous signal is far more likely to be interference, an instrumental artifact, or a known phenomenon than something genuinely new and strange. So the first task was to check systematically whether the signal could be explained by ordinary causes. The most likely ordinary explanation was terrestrial interference. Radio telescopes are plagued by interference from human sources, radio and television broadcasts, radar, electrical equipment, and countless other emitters of radio waves. Such interference can produce all sorts of spurious signals on the charts, and it is the bane of radio astronomers. The first suspicion, when an anomalous signal appears, is usually that it's interference. Bell and Hewish had to determine whether the pulsing signal could be a form of terrestrial interference. Several features of the signal argued against interference. The most important was its fixed position among the stars. The signal appeared when a particular part of the sky was overhead and disappeared when that part of the sky set, keeping pace with the stars rather than with terrestrial time. Interference from Earth would not generally behave this way. It would be tied to terrestrial sources and terrestrial schedules, not to the rotation of the celestial sphere. The signal's adherence to celestial timing strongly suggested a cosmic origin. To confirm this, the team could check whether the signal returned according to the sidereal time, the timekeeping system based on the stars which differs slightly from ordinary solar time. A genuine celestial source would reappear according to sidereal time, keeping its place among the stars as the Earth orbited the Sun. An interference source would more likely follow solar time, tied to the human day. The pulsing signal, when checked, followed sidereal time, returning in step with the stars. This was strong evidence that it was genuinely astronomical, not terrestrial interference. The team also had to rule out instrumental artifacts, spurious signals produced by the telescope or recording equipment itself. Electronic systems can generate their own signals through various malfunctions or quirks that might masquerade as cosmic sources. To check this, the team could examine whether the signal appeared in the way a genuine cosmic source would, with the right characteristics of how it entered and exited the telescope's field of view. The signal passed these checks, behaving like a real source on the sky rather than an internal artifact. Another possibility was that the signal came from within the solar system, from a spacecraft, perhaps, or some object reflecting radio waves. This too could be checked by examining the signal's position and behavior. The signal's fixed position among the distant stars, rather than moving against them as a nearby object would, argued against a solar system origin. It appeared to come from far beyond the solar system, from the realm of the stars. This made it a genuinely deep space signal, not something local. As these ordinary explanations were ruled out one by one, the situation became increasingly puzzling. The signal was not terrestrial interference. It kept sidereal time. It was not an instrumental artifact. It behaved like a real source. It was not a nearby object. It kept its place among the distant stars. The mundane explanations were failing and the signal remained, demanding to be explained. With each ruled-out possibility, the signal grew more mysterious, and the remaining explanations grew more extraordinary. This process of elimination is itself a kind of intellectual discipline, and it is worth dwelling on. It is tempting, when confronted with something strange and exciting, to leap to the most thrilling explanation. The team did not do this. They worked methodically through the boring possibilities first, interference, malfunction, local objects, precisely because these were the most likely. Only when each had been tested and found wanting did the extraordinary possibilities come into focus. This is the unglamorous machinery of good science, not the flash of inspiration, but the patient closing of doors, one after another, until only the surprising ones remain open. It was the systematic exclusion of ordinary explanations that brought the team, reluctantly, to consider extraordinary ones. They had not leapt to the conclusion of an alien signal. They had been driven toward it by the failure of the mundane alternatives. This is the proper scientific procedure, ruling out the ordinary before accepting the extraordinary. And as the ordinary explanations fell away, the team found themselves facing a signal that seemed to demand either a wholly new kind of natural object or an artificial intelligent source. The careful elimination of the obvious had led them to a genuinely strange place, a place where the only remaining explanations were ones that would, either way, change astronomy. They had not gone looking for the extraordinary. The extraordinary had been left standing after everything else had fallen. The detailed investigation of the signal required better equipment than the ordinary charts provided. The standard recording did not have enough time resolution to capture the fine structure of the signal, to reveal whether it was truly pulsing and if so, with what precise period. To investigate this, Hewish arranged for a faster recorder to be used, one that could capture the signal's behavior in finer temporal detail. This faster recording would reveal whether the signal really had the regular pulsing structure that the ordinary charts hinted at. But there was a complication. The signal was intermittent. It did not appear every time the relevant part of the sky was overhead. Sometimes it was there, and sometimes it was not. This intermittency made it difficult to capture with the faster recorder. The recorder had to be running at exactly the right time, when the signal was both present and the right part of the sky was overhead. For a period, this proved frustratingly difficult. The faster recorder would be set up and running, the right part of the sky would come overhead, and the signal would fail to appear. Night after night, the recorder ran and the signal stayed silent. This period of silence was trying. Bell had observed the signal on the ordinary charts, but without the detailed faster recording, its true nature remained uncertain. The intermittent appearances made it hard to pin down. There was a real possibility during this frustrating stretch that the signal would simply not return, leaving its nature forever unresolved, an unexplained anomaly, neither confirmed nor understood. The silent nights raised the worry that the opportunity to understand the signal might slip away. The intermittency also complicated the interpretation. A signal that came and went was harder to characterize than a steady one. Was the source itself intermittent, turning on and off? Or was it always emitting, but only sometimes detectable depending on conditions? These questions could not be answered without more detailed observations, which required catching the signal with the faster recorder. The intermittency was, in a sense, part of the puzzle, another strange feature of an already strange signal. Then, after the period of silence, the signal returned, and this time the faster recorder captured it. The detailed recording revealed the signal's true structure, a series of regular pulses spaced about 1 1/3 seconds apart, repeating with remarkable precision. This was the crucial observation. It confirmed that the signal was genuinely pulsing, with a stable, well-defined period. The faster recorder had captured what the ordinary charts could only hint at, the clockwork regularity that made the signal so extraordinary. The confirmation of the regular pulsing was a pivotal moment. It transformed the signal from a vague anomaly into a precisely characterized phenomenon. The pulses were real, regular, and astonishingly stable. This precise regularity was the feature that made the signal so puzzling and so suggestive of an artificial origin. With the faster recording in hand, Bell and Hewish could no longer dismiss the signal as a vague glitch. It was a real, regular, pulsing source demanding explanation. The successful capture of the signal also demonstrated the value of persistence. Through the frustrating silent nights, the team had kept trying, kept the recorder ready, kept watching for the signal's return. When it finally returned, they were ready to capture it. Had they given up during the silent period, the signal might have remained an unexplained anomaly. Their persistence paid off, allowing them to obtain the detailed observation that revealed the signal's true nature. Discovery often requires this kind of persistence, this willingness to keep trying through frustration and uncertainty. There is a particular cruelty to intermittent phenomena in science. A steady signal can be studied at leisure, an intermittent one must be caught in the act, and it does not cooperate with the observer's schedule. The faster recorder had to be running at exactly the right moment, on exactly the right patch of sky, when the signal happened to be present. For a stretch of nights, these conditions simply failed to align, and the team could do nothing but wait and try again. The eventual success was as much a matter of patience as of skill, a refusal to be discouraged by the signal's refusal to appear. With the regular pulsing confirmed, the investigation entered a new phase. The signal was now precisely characterized, and its extraordinary regularity demanded an explanation. The team faced the question they could no longer avoid. What could produce such a signal? The known natural processes seemed inadequate. And so, however reluctantly, they had to consider the possibility that the signal was artificial, that it might be a beacon from another civilization. The faster recorder had revealed a signal that, in its precision, seemed almost designed. The question of who or what had designed it now had to be confronted. The period of the pulses, about 1.337 seconds to be more precise, was a number that carried enormous significance. Its exact value, and more importantly its stability, was central to why the signal was so puzzling. To understand the reaction the signal provoked, one must understand why a period of this length, held this steadily, was so hard to explain by known astronomy. The period was short, Many astronomical phenomena vary on timescales of hours, days, years, or longer. A variation with a period of just over a second was unusually rapid. What kind of astronomical object could produce a signal varying this quickly? The known variable objects, stars that pulsed or varied in brightness, generally did so much more slowly. A period of about a second pointed to something small and rapidly changing, unlike the large, slowly varying objects that astronomers were familiar with. Second, and more importantly, the period was extraordinarily stable. The pulses came at the same interval over and over, with a precision that rivaled the best clocks. This stability was the truly remarkable feature. It's one thing for an object to vary with a period of about a second, it is another for it to maintain that period with clock-like precision, pulse after pulse, without drifting. This kind of stability is characteristic of very few processes. On Earth, it is characteristic of carefully engineered clocks and oscillators. In nature, it is rare. The combination of a short period and high stability was what made the signal seem almost artificial. The stability in particular suggested some kind of precise underlying mechanism, a stable oscillator, a regular rotation, something that could keep time with great accuracy. Most natural processes do not keep time this well. The precision of the signal seemed to call for a mechanism of unusual regularity, and the most familiar examples of such mechanisms were artificial, the clocks and transmitters built by intelligence. There was a tension here, though, that the team recognized. If the signal were a deliberate beacon from an alien civilization, intended as a message, one might expect it to carry information, to vary in some way that encoded content, like a coded transmission. But the signal did not seem to carry information in this sense. It was simply regular, the same pulse over and over, without obvious variation or encoding. A purely regular signal carrying no information was an odd kind of message. This argued somewhat against the idea of a deliberate communication, though it did not rule out other artificial origins, such as a beacon or a byproduct of some alien technology. The short, stable period also constrained the size of the source. A signal that varies rapidly must come from a small source, because of a basic physical principle. An object cannot vary coherently faster than light can travel across it. If an object is large, different parts of it cannot coordinate their behavior quickly, so it cannot produce rapid, sharp variations. The rapidity of the pulses implied that the source was small and much smaller than an ordinary star. This was another clue, pointing toward a compact, unusual object. Estimating from the sharpness of the pulses, the source had to be quite small by astronomical standards, perhaps only thousands of kilometers across, or even less. This was tiny compared to a normal star like the Sun, which is over 1 million kilometers across. A source this small, producing this much energy, varying this rapidly and regularly, was unlike any known astronomical object. The constraints from the period and pulse sharpness painted a picture of something genuinely new, a small, compact, precisely regular source of radio pulses. So the period of 1 1/3 seconds, held with such stability, was at the heart of the puzzle. It implied a small source, a precise mechanism, and a regularity unlike known natural objects. It was the feature that made the signal seem artificial, that raised the possibility of an intelligent origin, and that ultimately would point toward a new and astonishing kind of natural object. The number 1.337 seconds, short, stable, precise, was the key that, once understood, would unlock a new chapter in astronomy. But before that understanding came, it would lead the team into a brief but serious confrontation with the possibility of alien life. It is striking how much information was encoded in that single number. A period of about a second told astronomers that the source was small. The stability of that period told them it was a precise, steady mechanism. The sharpness of each pulse told them the source was smaller still. From the timing alone, the bare rhythm of the pulses, a great deal could be inferred about the nature of the object, long before anyone could see it or knew what it was. This is one of the quiet powers of physics, that a simple measurement, properly interpreted, can constrain reality so tightly. The pulses were, in a sense, a message after all, not from aliens but from physics, spelling out the properties of an object no one had ever seen. The link between regularity and intelligence is worth examining closely, because it is central to why the signal provoked thoughts of aliens. Why should a regular signal suggest an intelligent source? The answer lies in our experience of the world, and in a deep intuition about the difference between the products of nature and the products of design. In everyday experience, regular and precise patterns are typically the products of intelligence. A clock ticks regularly because it was designed to. A radio station broadcasts at a precise frequency because engineers built it to. A metronome keeps a steady beat because it was made for that purpose. Regularity and precision, in our experience, are hallmarks of design, signs that something was made by a mind for a purpose. Natural processes, by contrast, tend to be irregular, messy, variable. The wind does not blow in a regular rhythm. Rivers do not flow in precise pulses. Natural sounds are not metronomic. This intuition, that regularity implies design, is deeply ingrained, and it has a real basis. Many natural processes are indeed irregular, governed by chaotic or random dynamics that produce variable, unpredictable outputs. Achieving precise regularity often requires a special mechanism, and in our experience such mechanisms are usually designed. So when we encounter a regular precise pattern, our intuition reasonably suggests that it might be the product of intelligence. This intuition serves us well in many contexts, helping us distinguish the made from the merely natural. In the search for extraterrestrial intelligence, this intuition plays a central role. How would we recognize a signal from an alien civilization? The general idea is that such a signal would have features that distinguish it from natural sources, features suggestive of design. Regularity is one such feature. A signal that is too regular, too precise, too patterned to arise from natural processes might be a sign of intelligence. Narrow frequency bands, regular pulses, mathematical patterns, these are the kinds of features that searchers for alien signals look for, precisely because they seem to require design. The pulsing signal that Bell and Hewish detected had exactly these suggestive features. It was extraordinarily regular, with a precise and stable period. It was concentrated in a narrow frequency band. By the standard intuitions about how to recognize an artificial signal, it looked like a candidate. If one were searching for alien signals and detected this, one would have to take seriously the possibility that it was artificial. The signal matched, in important respects, the profile of what an intelligent beacon might look like. This is why the team, despite their scientific caution, could not entirely dismiss the possibility of an intelligent origin. The signal's features genuinely pointed in that direction by the standard reasoning about how to distinguish design from nature. It was not foolish or fanciful to consider the possibility. It was a reasonable response to a signal with these characteristics. The regularity that suggested intelligence was a real feature of the signal, and it demanded to be taken seriously, even if only to be eventually explained by other means. Of course, the intuition that regularity implies intelligence is not infallible. Nature can, in fact, produce regular patterns under the right circumstances. The orbits of planets are regular. The rotation of the Earth is regular. Certain physical oscillations are regular. The intuition is a useful guide, but not an absolute rule. Nature has its own ways of producing regularity, through stable physical processes like rotation and orbital motion. The challenge, when confronting a regular signal, is to determine whether it arises from such a natural process or from genuine design. This determination requires more than the intuition. It requires investigation. In the case of the pulsing signal, the investigation would eventually reveal a natural source, a kind of object whose regular rotation produced the precise pulses without any need for intelligence. But before that resolution came, the signal's regularity kept the possibility of intelligence on the table. It was a possibility grounded in sound reasoning about the signatures of design, even though it would ultimately prove to be wrong. The regularity suggested intelligence because regularity often does suggest intelligence, and it took careful work to discover that in this case, nature had found its own way to keep time with extraordinary precision. This points to a humbling truth about the search for intelligence in the cosmos. Our criteria for recognizing design are drawn from our experience of design on Earth, from clocks, transmitters, and machines. But the universe is under no obligation to respect the boundaries we have drawn between the made and the natural. It can produce, through blind physical law, the very signatures we take as marks of mind. The spinning neutron star keeps better time than most human clocks, yet it was never designed, never intended, never meant anything at all. The lesson is not that our intuitions about design are useless, but that they are provisional, guides to be tested against the strange inventiveness of nature, which has had billions of years to discover ways of being regular that owe nothing to intelligence. Faced with a signal they could not explain and unable to entirely dismiss the possibility of an artificial origin, the team gave the signal a name that has become legendary: LGM1, standing for Little Green Men 1. The name was half a joke, a piece of shorthand, but it captured the genuine, if remote, possibility that the signal might come from an extraterrestrial intelligence. The name has endured, becoming one of the most famous designations in the history of astronomy. The origin of the name was practical as much as whimsical. As Bell later explained, the team needed a shorthand way to refer to the signal. It was cumbersome to keep describing it by its coordinates, that pulsing source at right ascension, 19 hours 19 minutes, declination plus 20 degrees. A shorter name was needed for convenience. Little Green Men served this purpose while also acknowledging, with a wink, the possibility that the signal might be artificial. It was a label born partly of practicality and partly of the genuine puzzlement the signal caused. The accounts of who took the alien possibility most seriously vary somewhat. By Bell's own account, she did not genuinely believe the signal came from aliens. She found the idea more of a nuisance because it complicated the interpretation of her data. She was fairly confident that the signal had a natural explanation, even if she did not yet know what it was. Some accounts suggest that Hewish, her supervisor, took the artificial possibility more seriously, at least initially. The degree of genuine belief in the alien hypothesis differed among the people involved. But regardless of how seriously any individual took it, the possibility was real enough to be discussed and to influence the team's thinking. The signal's features genuinely suggested an artificial origin by the standard reasoning, and this could not simply be ignored. The name Little Green Men, however jokingly applied, reflected a genuine scientific situation, a signal that by its characteristics might be artificial, detected from space, demanding to be explained. The whimsy of the name should not obscure the genuine puzzlement underneath. The name also reflected the cultural context of the time. Little Green Men was a stock phrase for imagined aliens, drawn from science fiction and popular culture. By invoking it, the team connected their puzzling signal to the broader cultural fascination with extraterrestrial life. The phrase carried a certain irony, using a cliched image of aliens to label a signal that might, just might, actually be from aliens. This irony was part of the name's appeal, and part of why it stuck. There is something revealing in the choice of a humorous name for a potentially momentous discovery. Scientists often use humor to manage the tension of uncertainty, to acknowledge a remarkable possibility without committing to it prematurely. By calling the signal Little Green Men, the team could take the artificial possibility seriously enough to investigate it, while maintaining a healthy skepticism and not overcommitting to an extraordinary claim. The humor was a way of holding the possibility at arm's length, treating it seriously but not solemnly. As it turned out, the signal was not from Little Green Men. It had a natural explanation, which would soon be discovered. The name, in this sense, was a misnomer. The signal came not from aliens, but from a kind of star. But the name endured nonetheless, attached to the first of these objects and embedded in the history of their discovery. It commemorates the brief period when the possibility of an alien signal was genuinely on the table, before the natural explanation emerged. It is a reminder of how strange the signal seemed, and of the genuine uncertainty the team faced. The designation LGM-1 eventually gave way to a more formal name as the nature of the object became clear. The object is now known by a catalogue designation reflecting its position in the sky, but the name Little Green Men lives on in the lore of astronomy, a memorable piece of history attached to a momentous discovery. It captures, better than any technical designation, the drama of those weeks in 1967 when a graduate student and her supervisor confronted at a signal so precise that it seemed it might be a message from the stars. There is a lesson in the durability of the name. Technical designations are precise but forgettable. They convey information without conveying feeling. Little Green Men conveys feeling, the puzzlement, the wonder, the half-serious thrill of a possibility almost too large to contemplate. It is the name that captures what the moment actually felt like before the answer was known, and perhaps that is why it has endured while the formal designation is known mainly to specialists. We remember the names that carry the emotional truth of a moment, even when, especially when, the literal truth turned out to be otherwise. The signal was not from Little Green Men, but for a few weeks it might have been, and the name preserves that electric uncertainty forever. There was a darker undercurrent to the discovery that is sometimes overlooked. The genuine unease, even fear, that accompanied the possibility of a real detection of extraterrestrial intelligence. If the signal really was an alien beacon, The implications would be staggering for science, for society, for humanity's understanding of its place in the universe. This was not entirely a comfortable prospect, and it weighed on the people involved in ways that are worth considering. Bell later described the period as containing a degree of worry. She'd been working hard on her doctoral research, and the appearance of a possibly artificial signal threatened to complicate everything. If the signal were truly from aliens, her careful work on quasars would be overshadowed, and she would find herself at the center of something far larger and stranger than a doctoral thesis. There was a sense in which the alien possibility was an unwelcome intrusion, a complication she would rather not have had to deal with. But beyond the personal complications, there was a deeper unease about the implications of a real detection. The discovery of an extraterrestrial intelligence would be one of the most momentous events in human history. It would confirm that humanity was not alone, that other minds existed among the stars. The consequences, scientific, philosophical, religious, social, would be profound and unpredictable. To be the ones who made such a discovery would be to bear an enormous responsibility and to step into genuinely uncharted territory. There was also the question of what such a detection would mean about the aliens themselves. A civilization capable of sending signals across interstellar distances would be technologically advanced, probably far beyond humanity. The encounter with such a civilization, even at the distance of a radio signal, would force humanity to confront its own place in a cosmic hierarchy. Would the aliens be benign or hostile? Would contact be beneficial or dangerous? These questions, the stuff of science fiction, would suddenly become real if the signal proved to be artificial. The prospect was both thrilling and unsettling. The team also faced a practical and ethical question. What should they do if the signal really was artificial? How should such a discovery be announced? To whom? With what safeguards? The detection of an alien signal would not be an ordinary scientific result to be published in the usual way. It would be a momentous event with enormous implications, and handling it responsibly would require careful thought. The team had to consider these questions, at least preliminarily, during the period when the artificial possibility remained open. For Bell, there was a particular poignancy to the situation. She was a graduate student, relatively junior, suddenly confronting the possibility of a world-changing discovery. The weight of it, the responsibility, the uncertainty, these were a great deal to bear for someone at her career stage. She handled it with remarkable composure, continuing her careful work, neither dismissing the possibility nor being overwhelmed by it. But the strain was real. The quiet fear of a real detection was part of the emotional texture of those weeks. It is worth pausing to appreciate the strangeness of the situation. Here was a young scientist working on an ordinary doctoral project who found herself confronting one of the most profound possibilities imaginable, that she had detected a signal from another civilization. For a brief period before the natural explanation emerged, this possibility hung in the air. With all its staggering implications, the experience must have been disorienting, exhilarating, and frightening in roughly equal measure. Few scientists ever face such a moment. The fear, of course, turned out to be unnecessary. The signal was not artificial, it had a natural explanation. The momentous implications of an alien detection never materialized. But for those weeks in 1967, the possibility was real enough to provoke genuine unease, and to make the team think hard about what a real detection would mean. This emotional dimension, the quiet fear, the sense of standing at the edge of something enormous, is part of the human story of the discovery, often overshadowed by the eventual scientific explanation, but real and significant in its own right. The discovery was not just an intellectual puzzle, it was an emotional experience, charged with the weight of what might have been. It is easy, in retrospect, to forget this. We know how the story ends. We know the signal came from a neutron star, not a civilization, and so the alien possibility can seem, from our vantage, like a quaint misstep, a charming, false start. But the people living through it did not know how it would end. For them, the possibility was open, and its weight was real. To inhabit that uncertainty, to hold even briefly the thought that one might have heard from another mind in the cosmos, is something few human beings have ever experienced. The fear and the wonder were the appropriate responses to a genuinely open question, and they deserve to be remembered alongside the eventual answer. It is worth pausing to consider seriously what it would have meant if the signal really had been a message from another civilization. The team's brief consideration of this possibility was not idle speculation. It touched on one of the deepest questions humanity can ask. Imagining the consequences of a confirmed detection illuminates why the possibility, however remote, was taken seriously and treated with such care. The most immediate consequence would have been the answer to an ancient question: are we alone? For all of human history, this question has remained open. People have wondered whether other minds exist in the universe, whether life and intelligence are unique to Earth or common throughout the cosmos. A confirmed alien signal would have answered this question decisively. We would know for certain that we are not alone, that intelligence has arisen at least once elsewhere. This knowledge alone would transform humanity's understanding of its place in the universe. The scientific implications would have been enormous. A signal from an advanced civilization might carry information about their science, their technology, their understanding of the universe. Even a signal that carried no decipherable message would tell us that interstellar communication is possible, that civilizations can persist long enough to send signals across the vast distances between stars. The mere existence of the signal would be a data point of incalculable value, reshaping fields from astronomy to biology to the study of the long-term prospects of technological civilizations. The philosophical and religious implications would have been profound. Many human belief systems are built, implicitly or explicitly, around the idea of humanity's special place in the cosmos. The discovery of another intelligence would challenge these ideas, forcing a reconsideration of humanity's significance. Some traditions might absorb the discovery readily, others might be shaken by it. The cultural reverberations would spread through every society on Earth, touching the deepest questions of meaning and purpose. There would also have been practical and political questions. How should humanity respond to a signal? Should we reply? Who would speak for Earth? The detection of an alien civilization would raise unprecedented questions of governance and coordination, with no established framework for answering them. The team in 1967 was not equipped to handle these questions, and neither really was the world. A confirmed detection would have thrust humanity into a situation for which it was wholly unprepared. The distance to the source would have shaped the implications. The signal coming from among the distant stars would have originated far away, likely many light years distant, perhaps far more. This means the signal would have been old, having travelled for years or centuries to reach Earth. Any reply would take just as long to return. Communication, if it were possible at all, would unfold over timescales of years, centuries, or longer. The encounter would not be a conversation, but an exchange of messages across vast gulfs of time and space, with each side perhaps long changed by the time a reply arrived. There is also the sobering possibility that detecting the signal would tell us something uncomfortable. If the civilization that sent it had since vanished or destroyed by war, disaster, or the simple passage of time, then the signal would be a kind of message from the dead, a relic of a civilization no longer present. This possibility connects to deep questions about the longevity of technological civilizations, about whether intelligence tends to destroy itself, about the long-term prospects of our own species. Detected signal might be a warning as much as a greeting. This thought has a peculiar poignancy when one considers the timescales involved. A signal crossing interstellar distances takes years, centuries, sometimes millennia to arrive. By the time it reaches us, the civilization that sent it has had all that time to change, to evolve, perhaps to perish. We would be receiving a snapshot of a past that may no longer exist, light from a window that may long since have gone dark. In this sense, listening to the stars is a form of listening to history, to voices that may have fallen silent before we were born. The cosmos, for all its vastness, offers no guarantee that anyone is still there to answer. All of these implications were latent in the pulsing signal during the brief period when it might have been artificial. The team did not work them all out in detail. There was no time, and the natural explanation soon emerged. But the implications were there, hovering over the investigation, lending it a weight beyond the ordinary. To be right about an alien signal would have meant stepping into one of the most consequential moments in human history. That the signal turned out to be natural does not diminish the significance of what was briefly at stake. For a few weeks, a graduate student in Cambridge held in her charts the possibility of answering humanity's oldest question. Suppose the signal had been confirmed as artificial. How would such a discovery be announced? This question, which the team had to consider during the period of uncertainty, is more difficult than it might first appear. Announcing the detection of an extraterrestrial intelligence would be unlike any ordinary scientific announcement, fraught with risks and responsibilities that ordinary discoveries do not carry. The first problem is the risk of error. Extraordinary claims require extraordinary evidence, and the claim of detecting alien intelligence is about as extraordinary as they come. If the team announced such a detection and turned out to be wrong, if the signal proved to be interference or a natural phenomenon or an instrumental artifact, the damage to their credibility, and to science generally, would be severe. The history of science includes cautionary tales of premature claims that proved embarrassing. The team would have to be extremely confident before announcing anything, lest they cry wolf and discredit both themselves and the serious search for extraterrestrial intelligence. This created a tension. On one hand, the possibility of an alien signal demanded careful, thorough investigation before any announcement. On the other hand, the team could not investigate forever. At some point, if the signal really were artificial, the discovery would have to be shared. Balancing the need for certainty against the imperative to share a momentous discovery would be delicate. Announce too soon and risk being wrong. Wait too long and delay a discovery of immense importance. There was no obvious right answer. There was also the question of how the announcement would be received and managed. A confirmed alien detection would attract enormous public attention, with all the attendant risks of sensationalism, misunderstanding, and panic. The team would have to consider how to present the discovery responsibly, how to convey its significance without provoking undue alarm or fueling wild speculation. This would require careful communication, ideally with the input from beyond the immediate research team. Handling the public dimension of such a discovery would be a major challenge in itself. The team also had to consider to whom the discovery should be reported, and in what order. Should they inform their institution first, the government, international bodies, the scientific community, the public? The detection of an alien signal might have implications for national security, for international relations, for global society. The question of who should be informed and when did not have an established protocol in 1967. The team would have to navigate this without a map, making decisions with enormous potential consequences. Bell later reported that Hewish, at one point, called a meeting without her to discuss how the team should handle presenting their results. This detail is revealing. It shows that the team was actively grappling with the problem of announcement, taking seriously the possibility that they had something momentous on their hands. It also reflects the hierarchical and sometimes exclusionary nature of the scientific environment, in which a graduate student, even one central to the discovery, might be left out of key discussions. The dynamics of how the discovery would be handled were shaped by the social structures of science at the time. The problem of announcement also intersected with questions of credit and recognition. Who would be credited with the discovery? How would the contributions of different team members be acknowledged? These questions, which would later become contentious in the matter of the Nobel Prize, were latent even in the period of uncertainty. The handling of a momentous discovery involves not just scientific and public considerations, but also the human matters of credit, recognition, and fairness. These would prove significant in the aftermath of the actual discovery. In the event, the problem of announcing an alien signal never had to be fully solved, because the signal proved to be natural. The discovery that was eventually announced was the discovery of a new kind of star, not of an alien civilization. This was momentous in its own right, but it did not carry the same fraught implications as an alien detection would have. The team could announce it through the ordinary channels of science in a scientific paper, without the extraordinary precautions that an alien detection would have required. The natural explanation, in a sense, simplified the problem of announcement enormously. But the fact that the team had to consider these questions, even briefly, is part of the story. For a period, they faced the prospect of having to announce one of the most consequential discoveries in human history, with all its risks and responsibilities. The problem of announcing such a claim was real, and grappling with it was part of the experience of the discovery. That the problem dissolved when the natural explanation emerged does not erase the fact that for a time it loomed large. The resolution of the puzzle began with a crucial development. Bell found a second pulsing source in a completely different part of the sky. This discovery, made during her continued analysis of the charts, would prove decisive in ruling out the alien hypothesis. The appearance of a second source far from the first changed the interpretation fundamentally. Bell, continuing her careful analysis of the charts even as the first signal was being investigated, noticed another bit of scruff, another anomalous pulsing signal, but coming from a different direction entirely. This second source had its own period, distinct from the first, but it shared the same essential character: regular, precise pulses, repeating with clock-like stability. It was another example of the same strange phenomenon, but located in a different part of the sky. The discovery of the second source was, in its way, a relief. If there had been only one pulsing source, the alien hypothesis would have remained difficult to dismiss. A single artificial signal from a single location was at least conceivable as a beacon from a single civilization, but a second source, in a completely different part of the sky, was much harder to explain as artificial. It would require two separate civilizations, in two different directions, both happening to send similar signals, both happening to be detected at the same time. This seemed highly improbable. Bell herself recognized the significance immediately. As she later explained, the discovery of the second source made it very unlikely that the signals were artificial. It strained credulity to suppose that two different alien civilizations, in two different parts of the sky, would both be broadcasting similar regular signals, and that both would happen to be detected by the same telescope in the same period. Far more likely was that the signals came from a natural phenomenon, some kind of astronomical object that produced regular pulses and that existed in multiple locations throughout the galaxy. This reasoning illustrates an important principle in science: the power of multiple instances. A single anomaly is hard to interpret. It might be a fluke, an error, or something genuinely strange. But multiple instances of the same anomaly in different places point toward a general phenomenon, something that occurs repeatedly, according to natural laws, rather than a unique event. The second pulsing source transformed the puzzle from a possible unique signal into evidence of a general class of objects. This shift in interpretation was crucial. The second source also helped to rule out other mundane explanations. If the signal had been some kind of instrumental artifact or local interference, it would have been a strange coincidence for a second, similar signal to appear from a completely different direction. The appearance of multiple sources in different parts of the sky, behaving similarly, pointed toward a real astronomical phenomenon, distributed through space rather than a local or instrumental effect. The second source strengthened the case that the signals were genuinely cosmic and genuinely natural. Bell would go on to find still more pulsing sources, further confirming that the phenomenon was general. With each new source, the case for a natural explanation strengthened, and the case for an artificial one weakened. The signals were not unique beacons, but examples of a widespread class of astronomical objects. The galaxy, it seemed, was populated with these regular pulsing sources, scattered through space, all producing the same kind of clock-like signal. This was a remarkable discovery in its own right, even though it was not the discovery of aliens. It is worth noting the emotional arc of this moment for Bell herself. The alien possibility, for all its excitement, had been a kind of burden, a complication that threatened to derail her doctoral work and thrust her into something far larger and stranger than she had bargained for. The discovery of the second source lifted that burden. It meant that the signals were natural, that her work could proceed as science rather than spectacle, that she was dealing with stars rather than civilizations. There was relief in this, even as there was a different kind of wonder. She had not found aliens. She had found something new under the sun, a new kind of star, and that was discovery enough. The finding of the second source thus marked a turning point. It effectively ended the serious consideration of the alien hypothesis, redirecting the investigation toward natural explanations. The question was no longer, is this an alien signal? But, what kind of natural object produces these regular pulses? This was a different and more tractable question, one that astronomy could address with its established methods. The discovery of multiple sources had transformed a potentially world-changing and deeply uncertain situation into a fascinating but more ordinary scientific puzzle, the puzzle of identifying a new kind of star. And in solving that puzzle, astronomers would uncover an object every bit as extraordinary as the aliens would have been, in its own strange and silent way. The logic by which the second signal dissolved the alien hypothesis deserves closer examination, because it illustrates a beautiful piece of scientific reasoning. The shift from one source to two did not just add evidence, it fundamentally changed the most reasonable interpretation of the phenomenon. Understanding why reveals something deep about how scientists weigh competing explanations. Consider the situation with a single source. The signal was regular, precise, and seemingly artificial in character. Two broad explanations were possible: an artificial source, an alien beacon, or an unknown natural phenomenon. The artificial explanation, while extraordinary, could not be easily dismissed, because the signal's features genuinely suggested design. The natural explanation was preferable on grounds of conservatism, but no known natural object produced such signals, so it required positing something new. With a single source, the two explanations were difficult to weigh against each other. Both required something remarkable. Now consider the situation with two sources in different parts of the sky. The artificial explanation now requires two separate alien civilizations, independently producing similar signals, both detected at the same time. The probability of this is very low. Alien civilizations, if they exist, would presumably be rare and scattered. To have two of them in different directions, both broadcasting similar regular signals, both detected simultaneously by one telescope, would be an extraordinary coincidence. The artificial explanation, which was merely extraordinary for one source, becomes wildly improbable for two. The natural explanation, by contrast, becomes more plausible with two sources. If there is a natural phenomenon that produces regular pulsing signals, some kind of astronomical object, then it would be expected to occur in multiple locations throughout the galaxy. Finding two such sources in different parts of the sky is exactly what one would expect if the signals came from a class of natural objects. The natural explanation, which required positing a new phenomenon, is strengthened by the appearance of multiple instances, because a general natural phenomenon should produce multiple instances. So the second source shifted the balance decisively. For a single source, the artificial and natural explanations were both remarkable, and choosing between them was difficult. For two sources, the artificial explanation became wildly improbable, while the natural explanation became expected. The reasonable conclusion flipped, from "we cannot rule out an artificial origin" to "this is almost certainly a natural phenomenon." The addition of one more data point transformed the interpretation. This is an example of how the number of instances can be decisive in scientific reasoning. A single instance of a phenomenon is often ambiguous, open to multiple interpretations. Multiple instances, especially when they fit the pattern expected from a general natural process, point clearly toward that natural process. The logic is essentially probabilistic. The natural explanation predicts multiple instances, while the artificial explanation does not, so multiple instances favor the natural explanation. This kind of reasoning is fundamental to how scientists distinguish between competing hypotheses. There is a deeper lesson here about the nature of artificial versus natural signals. An artificial signal, produced by a specific intelligence for a specific purpose, would be expected to be unique, or at least rare and localized. A natural phenomenon, governed by physical laws that operate throughout the universe, would be expected to occur widely, wherever the conditions are met. So the distribution of a signal, whether it is unique or widespread, is itself evidence about its origin. A widespread signal occurring in many locations is more likely natural. A unique signal from a single location leaves the artificial possibility more open. This principle has a certain elegance, and it generalizes well beyond the case of pulsars. Whenever we encounter a phenomenon and wonder whether it is the product of design or of natural law, we can ask, does it occur once or many times? Is it confined to one place or distributed throughout space? Natural laws are universal. They produce their effects wherever conditions allow. Design is particular. It produces its effects where a designer chooses to act. The pattern of occurrence, universal or particular, widespread or localized, carries genuine information about the underlying cause. It is one of the most useful tools we have for distinguishing the works of nature from the works of mind. The pulsing signals, occurring in multiple locations and eventually found to be common throughout the galaxy, fit the profile of a natural phenomenon perfectly. They were not unique beacons, but examples of a widespread class of objects, distributed through space according to natural laws. This distribution was strong evidence for a natural origin, and it was the discovery of the second source that first revealed this distribution. Two signals changed everything because they revealed that the phenomenon was widespread, and a widespread phenomenon is the signature of nature, not of design. The aliens receded, and a new kind of star came into view. With the alien hypothesis effectively ruled out, the focus shifted entirely to natural explanations. The signals came from nature, not from civilization. But what natural object could produce such regular, precise, rapid pulses? This was a genuine puzzle, because no known astronomical object behaved this way. The answer would require recognizing a kind of star that had been predicted in theory but never before observed. The recognition that the signals were natural was, in a sense, a return to normal science. The brief dramatic possibility of an alien detection had given way to a fascinating but more ordinary scientific question: the identification of a new astronomical phenomenon. This was still a major discovery, a new kind of object never before seen, but it was the kind of discovery that astronomy was equipped to handle through its established methods of observation and theory. The extraordinary tension of the alien possibility had dissipated, replaced by the focused excitement of a new natural puzzle. The challenge was that the signal's characteristics were genuinely difficult to explain. The pulses were rapid, with periods of about a second, and extraordinarily regular. They were sharp, indicating a small source, and they were powerful, detectable across interstellar distances. What kind of object could be small, produce powerful radio pulses, and pulse with such rapid, precise regularity? The known categories of stars and other objects did not seem to fit. The source had to be something new, something with unusual properties. The key constraints were the rapidity and regularity of the pulses. As discussed earlier, the rapidity implied a small source, much smaller than an ordinary star. The regularity implied a stable, precise mechanism, something that could keep time with great accuracy. Together, these constraints pointed toward a small, dense object with some kind of regular, stable behavior. The most natural candidates for such behavior were rotation or vibration. A small object that rotated rapidly and regularly, or that vibrated with a stable period, could produce regular pulses. Astronomers considered both possibilities. A vibrating object, pulsating in size like some variable stars do, could produce regular variations. A rotating object, spinning rapidly, with some feature that swept past our line of sight once per rotation, could also produce regular pulses. The challenge was to determine which mechanism was at work and what kind of object could sustain it. The rapidity of the pulses, in particular, placed severe constraints. To pulse about once per second, an object would have to vibrate or rotate very fast, which required it to be very small and very dense. This line of reasoning led astronomers toward a particular kind of hypothetical object, an extremely dense, compact star, far smaller and denser than ordinary stars. Only such an object could rotate or vibrate fast enough to produce the rapid pulses, while being stable enough to maintain the precise regularity. The idea of such ultra-dense stars was not new. It had been proposed decades earlier, on theoretical grounds, though no such star had ever been observed. The pulsing signals seemed to point toward these long hypothesized objects. The theoretical prediction of ultra-dense stars went back to the 1930s, when physicists, working out the consequences of the new quantum mechanics and the physics of stellar collapse, had proposed that stars might end their lives as incredibly dense remnants. One proposed type was the neutron star, a star so dense that its matter was crushed into a sea of neutrons, packing the mass of a star into a sphere only a few kilometers across. These objects had been predicted in theory, but were thought to be perhaps undetectable, too small and faint to observe. The pulsing signals raised the possibility that neutron stars were not only real but detectable through the regular pulses they produced. So the resolution of the puzzle pointed toward one of the most exotic objects in theoretical astrophysics, the neutron star, a stellar remnant of extraordinary density, predicted decades earlier but never observed. If the pulsing signals came from neutron stars, then the discovery was not of aliens, but of something almost as remarkable. A new kind of star, representing matter in an extreme state, confirming theoretical predictions that had long awaited observational support. Nature, it turned out, was stranger than the alien hypothesis had supposed. The signals came not from little green men, but from the crushed corpses of dead stars. There is something fitting in this outcome. The team had been prepared, however reluctantly, to entertain the most extraordinary explanation they could imagine: intelligent beings signaling across the void. And yet the truth, when its aim, was not a retreat into the mundane. It was an advance into a different kind of strangeness, a kind of matter so dense that a thimbleful would outweigh a mountain, a kind of star so small it would fit inside a city, spinning so fast it completed a turn in the space of a heartbeat. The universe had not offered them aliens. It had offered them something that in 1967 was nearly as hard to believe. Once the signals were recognized as natural and the discovery was announced, a race began among theorists to explain exactly what kind of object produced the pulses and how. The announcement of the discovery in early 1968 set off a burst of theoretical activity as astrophysicists around the world tried to account for the remarkable signals. This period of intense theoretical work would quickly converge on the correct explanation. The discovery was announced in a scientific paper published in the journal Nature in February 1968. The paper reported the detection of the pulsing radio source, described its properties, and discussed possible explanations. It was a carefully written paper, presenting the remarkable observations while remaining cautious about their interpretation. The publication brought the discovery to the attention of the scientific community, and the response was immediate and intense. Astronomers and astrophysicists everywhere turned their attention to the puzzle of the pulsing sources. The central question was the mechanism of the pulses. What physical process could produce such rapid, regular, powerful pulses? Several hypotheses were proposed. One involved vibrating stars, specifically vibrating white dwarfs or neutron stars pulsating in size with a regular period. Another involved rotating stars with some feature that produced a pulse once per rotation. A third involved orbiting objects with the pulses produced by some effect related to the orbit. Each hypothesis had to be tested against the observed properties of the pulses. The key constraint again was the rapidity of the pulses. The periods were about a second, and some pulsars discovered shortly afterward had even shorter periods. To produce such rapid pulses, the mechanism had to operate very fast. This constraint quickly narrowed the possibilities. Vibrating white dwarfs, it turned out, could not vibrate fast enough to produce the most rapid pulses. Their natural vibration periods were too long. Orbiting objects would lose energy and spiral together too quickly to maintain stable periods. These hypotheses were gradually eliminated. The hypothesis that survived was rotation, specifically the rapid rotation of a neutron star. A neutron star, being extremely small and dense, could rotate very rapidly, completing a rotation in about a second or even faster, while remaining stable. If such a rotating neutron star had a feature that produced a beam of radiation, sweeping past our line of sight once per rotation, it would produce regular pulses with a period equal to the rotation period. This hypothesis could account for the rapidity, the regularity, and the stability of the pulses. It emerged as the leading explanation. The rotating neutron star hypothesis was developed and championed by the astrophysicist Thomas Gold, among others. Gold argued that the pulsars were rapidly rotating neutron stars, emitting beams of radiation from their magnetic poles, which swept across our line of sight as the star rotated, producing the observed pulses like the beam of a lighthouse sweeping past a distant observer. This model, which came to be known as the lighthouse model, could explain the key features of the pulses. It quickly gained acceptance as the correct explanation. The lighthouse model made testable predictions. If pulsars were rotating neutron stars, then their rotation should gradually slow over time as they lost energy, causing their pulse periods to lengthen slightly. This prediction could be tested by careful timing of the pulses over extended periods. When such timing was performed, the predicted slowing was observed. The pulse periods did lengthen gradually, consistent with a rotating neutron star losing energy. This confirmation strengthened the case for the lighthouse model considerably. The speed with which the correct explanation emerged is itself remarkable. The discovery was announced in February of 1968. By May of that year, the rotating neutron star model had been proposed and was gaining acceptance. In the space of a few months, astronomers had gone from a baffling, seemingly artificial signal to a coherent physical model involving one of the most exotic objects in theoretical physics. This rapid convergence reflects the power of theoretical astrophysics, which had already worked out decades earlier what neutron stars should be like. When the observations arrived, the theoretical framework was waiting to receive them. The pieces fell into place with a swiftness that testifies to how well the groundwork had been laid. So the race to explain the pulses converged within a matter of months on the rotating neutron star model. The pulses came from rapidly sending neutron stars, beaming radiation from their magnetic poles, sweeping past our line of sight like cosmic lighthouses. This explanation accounted for all the key features of the signals and made predictions that were confirmed by observation. The puzzle of the pulsing sources was solved, not by invoking aliens, but by recognizing a new kind of star, exotic beyond what the alien hypothesis had imagined. The race had ended in a triumph of astrophysical reasoning, and a new field of astronomy was born. To understand what a neutron star is, and why it can produce the pulses, we need to understand the idea of a collapsed star. A star that has exhausted its fuel and collapsed under its own gravity into an extraordinarily dense remnant. This idea, which underlies the explanation of pulsars, is one of the most remarkable in astrophysics, describing matter in states of almost unimaginable extremity. Stars shine by nuclear fusion, converting light elements into heavier ones in their cores and releasing energy in the process. This energy produces an outward pressure that balances the inward pull of the star's own gravity, keeping the star stable. For most of a star's life, this balance holds. Gravity pulls inward, fusion pressure pushes outward, and the star maintains a stable size. But fusion cannot continue forever. Eventually, the star exhausts its nuclear fuel, and the balance is disrupted. When a star runs out of fuel, the outward pressure from fusion ceases, and gravity, no longer balanced, takes over. The star collapses inward under its own weight. What happens next depends on the star's mass. For a star like the Sun, the collapse is halted at a certain point by a quantum mechanical effect, leaving behind a dense remnant called a white dwarf, about the size of the Earth but containing the mass of a star. White dwarfs are dense, but they are not the densest possible remnants. For more massive stars, the collapse goes further. The gravity is strong enough to overcome the effect that halts the collapse in white dwarfs, and the star collapses to an even denser state. In this collapse, the electrons and protons of ordinary matter are forced together, combining to form neutrons. The result is a neutron star, an object composed almost entirely of neutrons, packed together at incredible density. The collapse to a neutron star is often accompanied by a supernova explosion, in which the outer layers of the star are blown away, leaving the dense neutron star core behind. The densities involved are almost beyond comprehension. A neutron star packs roughly the mass of the Sun, or more, into a sphere only about 20 kilometers across, the size of a city. The matter is compressed to the density of an atomic nucleus, the densest stable form of matter known. A teaspoon of neutron star material would weigh billions of tons. The gravity at the surface is enormous, billions of times stronger than Earth's. These are objects of extreme physics, where matter is pushed to the limits of what is possible. The idea of neutron stars was proposed in the 1930s, shortly after the discovery of the neutron itself. Physicists working out the consequences of stellar collapse realized that, for sufficiently massive stars, the collapse could produce these incredibly dense neutron stars. The prediction was a triumph of theoretical physics, applying the new understanding of nuclear physics and stellar structure to the fate of dying stars. But for decades, neutron stars remained purely theoretical. They were thought to be too small and faint to observe directly, perhaps forever beyond the reach of telescopes. This is why the discovery of pulsars was so significant. The pulsing signals provided the first observational evidence that neutron stars actually existed. The rapid, regular pulses could be explained by rotating neutron stars, and the properties of the pulses matched what such stars should produce. After decades as a theoretical prediction, neutron stars were finally observed, not directly as points of light, but through the regular radio pulses they emitted. The discovery confirmed one of the boldest predictions of theoretical astrophysics. The collapsed star, then, is the key to understanding pulsars. A pulsar is a neutron star, the collapsed remnant of a massive star, crushed by gravity into a city-sized ball of neutrons, of almost inconceivable density. It is the corpse of a star left behind after the star exhausted its fuel and collapsed, often in a supernova explosion. That such objects exist, and that they produce the regular pulses detected in 1967, is one of the remarkable facts that the discovery of pulsars revealed. The signal that briefly seemed to come from aliens came, in fact, from the crushed remains of a dead star, a phenomenon stranger, in its way, than the aliens would have been. It is worth dwelling on the chain of reasoning that connects a dying star to a regular radio pulse. A massive star exhausts its fuel. Gravity, no longer balanced by the pressure of fusion, crushes the core. The core collapses, its rotation speeding up and its magnetic field intensifying as it shrinks. The result is a tiny, dense, rapidly spinning, intensely magnetic object beaming radiation from its poles. As it spins, the beam sweeps across space, and once per rotation it crosses the Earth, producing a pulse. Each link in this chain is a consequence of well-understood physics, and together they explain how the death of a star gives rise to the clock-like ticking that Bell detected. The pulse is, in effect, the heartbeat of a corpse, a regular signal produced by an object that is, by any ordinary definition, dead. Let us look more closely at what a neutron star actually is, because these objects are so extreme that they strain the imagination. A neutron star is a state of matter unlike anything in ordinary experience, governed by physics pushed to its limits. Understanding its nature helps to appreciate both how it produces the pulses and how remarkable the discovery of pulsars truly was. A neutron star is composed almost entirely of neutrons, the neutral particles that, along with protons, make up the nuclei of ordinary atoms. In ordinary matter, neutrons exist only inside atomic nuclei, bound together with protons, but in a neutron star the matter has been compressed so severely that the ordinary structure of atoms has been destroyed. The electrons have been forced into the protons, combining to form neutrons, and the result is a vast assemblage of neutrons packed tightly together. The whole star is in effect like a single enormous atomic nucleus, held together by gravity rather than nuclear forces. The density of this neutron matter is staggering. In ordinary matter, atoms are mostly empty space, with tiny nuclei separated by relatively vast distances, surrounded by clouds of electrons. In a neutron star, this empty space has been eliminated. The matter is packed at nuclear density, with neutrons touching neutrons. This is the densest stable form of matter known to physics. The density is so great that, as mentioned, a teaspoon of neutron star material would weigh billions of tons, more than a mountain on Earth. It is difficult to truly grasp such a density. It lies far outside ordinary experience. The size of a neutron star is correspondingly small. Despite containing the mass of a star, typically more than the mass of the Sun, a neutron star is only about 20 kilometers across, the size of a city. This combination of enormous mass and tiny size produces extreme gravity. The gravitational pull at the surface of a neutron star is billions of times stronger than at the surface of the Earth. An object falling onto a neutron star would be accelerated to a significant fraction of the speed of light. The gravity is so strong that it noticeably warps space and time around the star, producing effects described by Einstein's general relativity. The structure of a neutron star is thought to be layered, with different states of matter at different depths. The outer layer, or crust, is a solid lattice of nuclei, extraordinarily rigid. Beneath the crust, the matter becomes increasingly neutron-rich and exotic. In the core, the matter may take forms that are not fully understood, possibly involving exotic particles or states of matter that cannot be produced or studied on Earth. The interior of a neutron star is a frontier of physics, where matter exists under conditions impossible to replicate in any laboratory. Neutron stars also have extreme magnetic fields and rapid rotation, both of which are crucial to their behavior as pulsars. The magnetic field of a neutron star can be trillions of times stronger than Earth's magnetic field, among the strongest magnetic fields in the universe. The rotation can be extremely rapid, with some neutron stars spinning hundreds of times per second. These extreme properties arise from the collapse that formed the neutron star, which concentrated and amplified the magnetic field and the rotation of the original star. Together, the strong magnetic field and rapid rotation produce the beamed radiation that we observe as pulses. The temperature of a young neutron star is also extreme, millions of degrees, though this is not directly responsible for the radio pulses. Neutron stars cool over time, but they remain hot for a long while after their formation. The combination of extreme density, gravity, magnetic field, rotation and temperature makes neutron stars among the most extreme objects in the universe. Laboratories of extreme physics, where matter and fields exist under conditions found nowhere else. They are natural experiments in the physics of the extreme, accessible to us only through the radiation they emit. That such objects exist, and that they are relatively common in the galaxy, is one of the remarkable facts revealed by the discovery of pulsars. Before 1967, neutron stars were a theoretical possibility, unconfirmed and perhaps unconfirmable. After the discovery, they were established as real observable objects scattered throughout the galaxy. The pulsing signal that briefly seemed to come from aliens came, in fact, from one of these extraordinary objects, a city-sized ball of neutron matter, spinning rapidly, beaming radiation across the cosmos. The reality was stranger, and in its way more wonderful than the alien hypothesis had imagined. Theory had described these objects in advance, but it took a bit of scruff on a chart to prove they were really there, turning in the dark. To grasp the extremity of a neutron star, it helps to dwell on the comparison that gives this section its title, the idea of crushing the mass of the Sun into a sphere the size of a city. This image, though almost impossible to truly comprehend, captures the essence of what a neutron star is, an object of stellar mass compressed to urban dimensions. Working through the comparison helps to make the abstraction concrete. The Sun is enormous. It contains about 99.8% of all the mass in the solar system. Its diameter is about 1.4 million kilometers, large enough to contain over 1 million Earths. It is a vast ball of hot gas, held together by its own gravity, generating energy through nuclear fusion in its core. By any human standard, the Sun is immense, a body of overwhelming scale. It is the dominant object in our cosmic neighborhood, and everything in the solar system orbits it. Now imagine taking all that mass, the entire mass of the Sun, or even somewhat more, and compressing it into a sphere only about 20 kilometers across. 20 kilometers is a distance one could drive in a few minutes, the size of a city. The mass that fills a sphere over 1 million kilometers in diameter is squeezed into a sphere the size of a metropolitan area. This is what happens in the formation of a neutron star. The core of a massive star containing more mass than the Sun collapses to this city-size scale. The compression is almost beyond imagining. The resulting density is what makes neutron stars so extreme. When you pack that much mass into that smaller volume, the density becomes enormous, equal to the density of an atomic nucleus, the densest stable matter known. Every cubic centimeter of a neutron star contains hundreds of millions of tons of matter. The familiar image is that a sugar cube-sized piece of neutron star material would weigh as much as a mountain, or as much as all of humanity combined. The matter is compressed beyond anything achievable on Earth, beyond anything in ordinary experience. The gravity that results from this compression is correspondingly extreme. On the surface of a neutron star, gravity is billions of times stronger than on Earth. If you could somehow stand on a neutron star, which you could not as the gravity would instantly crush you, your weight would be billions of times what it is on Earth. An object dropped from a small height above the surface would hit it at an enormous speed, having been accelerated by the crushing gravity. The escape velocity from a neutron star is a significant fraction of the speed of light. These are conditions of gravity unlike anything in the familiar universe. The compression also dramatically affects the star's rotation and magnetic field through the conservation of angular momentum and magnetic flux. When the core of a star collapses to neutron star dimensions, its rotation speeds up enormously, just as a spinning figure skater speeds up when pulling in their arms. A star that rotated slowly over days or weeks can become a neutron star rotating in a fraction of a second. Similarly, the magnetic field is concentrated and amplified by the collapse, becoming trillions of times stronger than Earth's field. These amplified properties, rapid rotation and intense magnetism, are precisely what enable the neutron star to produce the pulses we observe. The image of crushing the Sun into a city is, in the end, a way of conveying the almost incomprehensible nature of these objects. They are real. There are many of them in the galaxy, but they are so far outside ordinary experience that we can grasp them only through such comparisons. A city-sized object with the mass of a star, with gravity billions of times Earth's, spinning in a fraction of a second with a magnetic field of unimaginable strength. This is a neutron star. And it was such an object that produced the pulsing signal detected in 1967. There is something humbling in the realization that such objects exist, scattered throughout the galaxy, the remnants of dead stars. They represent matter pushed to the very edge of what physics allows, gravity concentrated to almost the point of forming a black hole. They are among the most extreme stable objects in the universe, and the discovery that they exist, that the predictions of the 1930s were correct, came from a graduate student noticing a bit of scruff on a chart, a regular pulse that turned out to be the heartbeat of one of these crushed stellar corpses. The mundane circumstance of the discovery and the extremity of the object discovered form a striking contrast. One of the most important properties of a neutron star, for understanding how it produces pulses, is its rapid rotation. Neutron stars spin extraordinarily fast, some completing a rotation in about a second, others in a fraction of a second, and the fastest in mere milliseconds. This rapid rotation is a direct consequence of the collapse that forms the neutron star, and it is governed by a fundamental physical principle, the conservation of angular momentum. Angular momentum is a measure of an object's rotational motion, depending on how fast it spins, how massive it is, and how its mass is distributed. A fundamental law of physics states that angular momentum is conserved. It cannot be created or destroyed, only transferred. For a rotating object that contracts with no external influences, the conservation of angular momentum requires that as the object gets smaller, it must spin faster. This is the principle that makes a spinning figure skater speed up when they pull in their arms. As their mass moves closer to the axis of rotation, their spin rate increases to conserve angular momentum. This same principle applies dramatically to the collapse of a star into a neutron star. The original star before collapse rotates slowly, perhaps once every few days or weeks, like the Sun. The star's core, which will become the neutron star, shares in this slow rotation. But when the core collapses, shrinking from a size comparable to the Earth, or larger down to the 20-kilometer scale of a neutron star, the conservation of angular momentum demands that its rotation speed up enormously. The dramatic reduction in size produces a dramatic increase in spin rate. The magnitude of the speed up is striking. A stellar core rotating once every few days, collapsing to neutron star dimensions, would end up rotating many times per second. The factor by which the rotation speeds up depends on the factor by which the size decreases, and since the collapse reduces the size by a huge factor, the rotation speeds up by a correspondingly huge factor. A slow stellar rotation becomes a rapid neutron star rotation, all as a consequence of the conservation of angular momentum during collapse. The slow turning of a giant star becomes the blur of a spinning neutron star. This rapid rotation is essential to the pulsar phenomenon. The pulses we observe are produced once per rotation, as a beam of radiation sweeps past our line of sight. The period of the pulses is therefore the rotation period of the neutron star. The fact that the pulses have periods of about a second or less reflects the rapid rotation of the neutron stars producing them. Without the rapid rotation, there would be no rapid pulses. The speed of the rotation is what makes the pulsar tick as fast as it does. The rotation of a neutron star is also extremely stable, which is why the pulses are so regular. A spinning neutron star is like an enormous flywheel, its rotation maintained by its angular momentum. There is little to disturb its spin, so it rotates with great steadiness, maintaining a precise period over long times. This rotational stability is the source of the clock-like regularity of the pulses. The neutron star is, in effect, a precise natural clock, its ticks marked by the sweeping of its radiation beam, kept regular by the steadiness of its rotation. Over very long times, the rotation does gradually slow, as the neutron star loses energy through its radiation and other processes. This slowing is slight but measurable, and it causes the pulse period to lengthen gradually over time. The observation of this gradual slowing was one of the confirmations of the rotating neutron star model, as discussed earlier. The slowing is slow enough that over human timescales the pulses remain remarkably regular, but over astronomical timescales the neutron star's rotation gradually winds down and eventually the pulsar fades. So the rapid spin of a neutron star, which is central to its behavior as a pulsar, comes from the collapse that forms it, through the conservation of angular momentum. The slow rotation of a dying star becomes the rapid rotation of a neutron star, which produces the rapid pulses we observe. This connection between collapse, conservation of angular momentum, and rapid rotation is one of the elegant pieces of physics underlying the pulsar phenomenon. The signal that briefly seemed to come from aliens was, in fact, marked out by the spin of a collapsed star, a spin inherited and amplified from the slow turning of the star that died to create it. The same law that makes a skater spin faster as she draws in her arms makes a dead star spin hundreds of times faster than the living one that preceded it, a humble principle scaled up to the grandeur of the cosmos. Alongside its rapid rotation, a neutron star possesses an extraordinarily strong magnetic field, and this field is the second key ingredient in producing the pulses. The magnetic field channels and accelerates charged particles, generating the beams of radiation that sweep across space. Understanding the origin and role of this magnetic field completes the picture of how a neutron star functions as a pulsar. Magnetic fields are common in stars. The Sun has a magnetic field produced by the motion of charged material in its interior, and this field drives much of the Sun's activity, from sunspots to solar flares. When a star collapses to form a neutron star, its magnetic field, like its rotation, is dramatically affected by the collapse. The principle involved is the conservation of magnetic flux, a tendency for the magnetic field to be carried along with the collapsing material, becoming concentrated as the material is compressed. As the stellar core collapses to neutron star dimensions, its magnetic field is concentrated into a much smaller volume. Just as the rotation speeds up when the size decreases, the magnetic field strengthens when it is compressed into a smaller area. The reduction in size by a large factor concentrates the magnetic field by a correspondingly large factor. The result is a magnetic field of enormous strength, trillions of times stronger than Earth's magnetic field, among the strongest magnetic fields known in the universe. The dead star carries an intense magnetic legacy from the star that formed it. The strength of these magnetic fields is difficult to convey. Earth's magnetic field, which is strong enough to orient a compass needle, is feeble compared to a neutron star's. The fields of neutron stars are so strong that they would be lethal at close range, disrupting the matter of any object that approached. In some extreme neutron stars, called magnetars, the fields are even stronger, strong enough to affect the structure of atoms and to power dramatic outbursts of radiation. The magnetic fields of neutron stars represent another way in which these objects push physics to its extremes. The magnetic field plays a crucial role in producing the pulsars. Charged particles near the neutron star, electrons and other particles, are caught up in the intense magnetic field and accelerated to enormous speeds, approaching the speed of light. As these charged particles are accelerated along the magnetic field lines, they emit radiation. This radiation is concentrated near the magnetic poles of the neutron star, where the field lines converge, and it is beamed outward in narrow cones along the magnetic axis. The result is two beams of radiation emanating from the two magnetic poles, like searchlights pointing in opposite directions. A key feature is that the magnetic axis of a neutron star is generally not aligned with its rotation axis. Just as the Earth's magnetic poles do not coincide with its geographic poles, a neutron star's magnetic poles are typically offset from its rotational poles. This misalignment is essential to the pulsar phenomenon. Because the magnetic axis is tilted relative to the rotation axis, the beams of radiation, which point along the magnetic axis, sweep around as the star rotates. The beams trace out cones in space as the neutron star spins, like the beams of a rotating lighthouse. This sweeping of the beams is what produces the pulses we observe. As the neutron star rotates, its radiation beams sweep across the sky. If one of the beams happens to sweep across the Earth, we detect a pulse of radiation each time the beam points in our direction, once per rotation. Between pulses, when the beams point away from us, we detect nothing. The result is a series of regular pulses, one per rotation, as the beam sweeps past us repeatedly. This is the essence of the lighthouse model, with the magnetic field providing the beams that the rotation sweeps around. So the magnetic field of the dead star, concentrated and amplified by the collapse, generates the beams of radiation that, swept around by the star's rotation, produce the pulses. The magnetic field and the rotation work together. The rotation provides the sweeping motion, and the magnetic field provides the beams that are swept. Together, they turn the neutron star into a cosmic lighthouse, emitting regular pulses of radiation. The signal detected in 1967 was produced by exactly this mechanism, the magnetic field of a collapsed star channeling radiation into beams, swept around by the star's rapid rotation, sweeping past the Earth once every 1 1/3 seconds. Two distinct properties, both inherited from the dying star and both amplified beyond all recognition by its violent collapse, conspire together to produce the steady ticking that a graduate student would one day notice on a roll of chart paper. The lighthouse model, which explains the pulses as the result of a rotating beam sweeping past the Earth, is worth dwelling on because it is both elegant and illuminating. The analogy to a lighthouse captures the essence of how a pulsar works, and it explains many of the observed features of pulsars in an intuitive way. Understanding this model fully resolves the mystery of the regular pulses. Consider an ordinary lighthouse. It has a light that shines in a particular direction, and the light rotates, sweeping its beam around the horizon. To an observer at sea, the lighthouse appears to flash. The beam sweeps past, producing a flash of light, then sweeps away, leaving darkness, then comes around again for another flash. The observer sees a regular series of flashes, one for each rotation of the lighthouse beam. The light is actually shining continuously, but the observer sees it only when the beam points in their direction. A pulsar works in the same way. The neutron star emits beams of radiation from its magnetic poles, and these beams sweep around as the star rotates. To an observer on Earth, the pulsar appears to pulse, the beam sweeps past, producing a pulse of radiation, then sweeps away, then comes around again for another pulse. The observer detects a regular series of pulses, one for each rotation of the neutron star. The radiation is actually being emitted continuously, but the observer detects it only when a beam points toward the Earth. The pulsing is a consequence of the sweeping beam, not of any actual pulsation of the source. This model elegantly explains the regularity of the pulses. The pulses are regular because the rotation of the neutron star is regular. The period of the pulses equals the rotation period of the star. Since the neutron star rotates with great steadiness, maintaining a precise period, the pulses are correspondingly regular. The clock-like precision of the pulses, which had seemed so puzzling and so suggestive of an artificial origin, is simply a reflection of the steady rotation of the neutron star. Nature, through the steady spin of a collapsed star, produces a regularity that rivals the best clocks. The model also explains why we do not detect all neutron stars as pulsars. For us to detect the pulses, one of the beams must sweep across the Earth. But the orientation of a neutron star's beams is random, depending on the alignment of its magnetic and rotation axes and the direction it happens to point relative to us. For many neutron stars, the beams never sweep across the Earth, and so we never detect their pulses, even though they are emitting radiation. We detect only those neutron stars whose beams happen to sweep across our location. This means that the pulsars we observe are only a fraction of the total population of neutron stars. Many more exist, beaming in directions that never cross our path. The lighthouse model further explains the sharpness of the pulses. The beams of radiation are narrow, concentrated near the magnetic poles. As a narrow beam sweeps past the Earth, it produces a brief sharp pulse. The radiation is detected only during the short interval when the beam points nearly toward us. The narrowness of the beam corresponds to the sharpness of the pulse. This sharpness was one of the features that indicated a small source, consistent with the compact size of a neutron star. The geometry of the sweeping beam accounts for the brief, sharp pulses observed. There is something poetic in the image of the pulsar as a lighthouse in the dark. Scattered throughout the galaxy, these collapsed stars spin in the darkness, sweeping their beams across the cosmos. Most of the time their beams point elsewhere and they go undetected. But occasionally a beam happens to sweep across the Earth and we detect a pulse, a brief flash of radiation from a distant dead star spinning in the void. The galaxy is full of these cosmic lighthouses, their beams sweeping silently through space, occasionally crossing our path and announcing their presence with a regular pulse. The lighthouse model, developed in the months after the discovery, resolved the mystery of the pulsing signals. The pulses came not from aliens, nor from any pulsation of the source, but from the sweeping of a beam, produced by a rotating neutron star. The model accounted for all the key features of the pulses, their regularity, their sharpness, the fact that we detect only some neutron stars as pulsars. It was a triumph of astrophysical reasoning transforming a baffling mystery into an understood phenomenon. The lighthouse in the dark was the answer to the riddle of the little green men, and a more beautiful answer in the end than the riddle had seemed to promise. The geometry of why the beam sweeps past us, and what determines whether we see a pulsar at all, deserves a closer look. It involves the interplay between the rotation axis, the magnetic axis, and our line of sight, a three-way geometric relationship that determines whether and how we detect a given neutron star's pulses. Understanding this geometry deepens our appreciation of the lighthouse model. Recall that a neutron star has two relevant axes, its rotation axis, around which it spins, and its magnetic axis, along which its radiation beams point. These two axes are generally misaligned, making some angle with each other. The radiation beams point along the magnetic axis, in two opposite directions from the two magnetic poles. As the star rotates around its rotation axis, the magnetic axis, and therefore the beams, sweep around, tracing out cones in space. The half angle of each cone is equal to the angle between the rotation and magnetic axes. Now consider our line of sight from the Earth to the neutron star. Whether we detect the pulsar depends on whether our line of sight falls within the cone traced out by one of the beams. If our line of sight lies within the cone, then once per rotation, as the beam sweeps around, it will point directly at us, and we will detect a pulse. If our line of sight lies outside the cone, the beam will never point at us, and we will never detect a pulse, even though the neutron star is emitting radiation. The geometry of our line of sight relative to the cone determines whether we see the pulsar. This geometric requirement means that we detect only a fraction of the neutron stars that exist. For a given neutron star, whether its beam sweeps across the Earth depends on the orientation of its axis and our viewing angle, essentially a matter of chance. Some neutron stars happen to be oriented so that their beams sweep across us, and we detect them as pulsars. Others are oriented so that their beams never cross our line of sight, and we never detect their pulses. The neutron stars we observe as pulsars are those that happen to be favorably oriented. Many more exist that we cannot detect by their pulses. The fraction of neutron stars we can detect depends on the typical geometry of the beams. If the beams are wide, sweeping out large cones, then a large fraction of neutron stars will have beams that cross our line of sight, and we will detect many of them. If the beams are narrow, sweeping out small cones, then only a small fraction will be detectable. The actual beams are relatively narrow, so we detect only a modest fraction of the neutron star population as pulsars. The rest remain hidden, their beams pointing in directions that never reach us. The geometry also affects the appearance of the pulses. The shape and duration of each pulse depend on how our line of sight cuts through the beam. If our line of sight passes through the center of the beam, we see a strong, well-defined pulse. If it passes through the edge of the beam, we see a weaker, possibly differently shaped pulse. The detailed structure of the observed pulses carries information about the geometry of the beam and our viewing angle, which astronomers can use to study the structure of the neutron star's radiation. Some pulsars show evidence of both beams from the two opposite magnetic poles. If the geometry is right, our line of sight might cross both beams during each rotation, producing a main pulse and a weaker secondary pulse called an interpulse, halfway between the main pulses. The presence of an interpulse indicates a particular geometry in which both poles' beams sweep across our line of sight. The observation of interpulses in some pulsars provides further confirmation of the lighthouse model and additional information about the geometry of these objects. So the sweeping of the beam past us, and whether it sweeps past us at all, is a matter of geometry, the orientation of the neutron star's axis relative to our line of sight. This geometry determines which neutron stars we detect as pulsars and how their pulses appear. It is a reminder that what we observe is shaped not only by the nature of the objects themselves, but by our particular vantage point. The pulsars we see are those that happen to beam in our direction. The galaxy holds many more, spinning in the dark, their beams forever pointed elsewhere. We catch only those whose light by chance sweeps across our small corner of the cosmos. For every pulsar we detect, there may be many we never will, silent to us not because they are quiet, but because their light was never aimed our way. The extraordinary regularity of pulsar pulses makes them among the most precise natural clocks in the universe. This timekeeping precision, which initially made the signal seem artificial, turned out to be one of the most scientifically valuable properties of pulsars. The clock at the heart of the star has become a powerful tool for astronomy and physics, used in ways that the original discoverers could hardly have imagined. The regularity of the pulses comes, as we have seen, from the steady rotation of the neutron star. A neutron star is an enormous, dense flywheel, spinning with great steadiness, little disturbed by external influences. Its rotation period is extremely stable, maintained with high precision over long times. Because the pulses are produced once per rotation, they inherit this stability, arriving at precisely regular intervals. Some pulsars, particularly the rapidly rotating ones called millisecond pulsars, keep time with a precision that rivals the best atomic clocks made by humans. This precision has made pulsars invaluable as timekeeping tools. By carefully measuring the arrival times of pulses, astronomers can use pulsars as clocks, tracking the passage of time with great accuracy. The stability of the pulsar clock allows for extraordinarily precise measurements, sensitive to tiny effects that would otherwise be undetectable. The pulsar's clock, ticking away at the heart of the spinning neutron star, provides a natural standard of time that astronomers can exploit for a variety of purposes. One application is the study of the neutron star itself. By timing the pulses precisely over long periods, astronomers can detect the gradual slowing of the rotation as the neutron star loses energy. They can also detect sudden changes in the rotation, called glitches, in which the rotation rate abruptly increases, events thought to be related to processes in the neutron star's interior. The precise timing of the pulses thus provides a window into the physics of the neutron star. revealing details of its rotation and internal structure that could not be observed any other way. Another application is the detection of companions. If a pulsar is orbited by another object, a planet, a star, or another neutron star, the orbital motion causes slight variations in the timing of the pulses as the pulsar moves toward and away from us in its orbit. By detecting these timing variations, astronomers can infer the presence of companions and measure their properties. This technique has been used to discover planets orbiting pulsars and to study binary systems containing pulsars. The precise pulsar clock reveals the gravitational influence of unseen companions through the subtle timing variations they produce. Perhaps the most remarkable application is the use of pulsars to test fundamental physics, including Einstein's theory of general relativity. In binary systems containing pulsars, the precise timing of the pulses allows astronomers to measure relativistic effects, subtle changes in the orbit and the pulse arrival times predicted by general relativity. These measurements provide some of the most stringent tests of the theory, confirming its predictions to high precision. The pulsar clock in these systems becomes a tool for probing the nature of gravity itself in regimes far more extreme than anything accessible on Earth. The precision of pulsar timing also enables the detection of gravitational wave ripples in spacetime predicted by general relativity. By monitoring an array of pulsars across the sky and looking for correlated variations in their timing, astronomers can search for the subtle effects of passing gravitational waves. This technique, using pulsars as a galaxy-sized detector, is sensitive to gravitational waves of very long wavelength, complementing other methods of gravitational wave detection. The pulsar clocks, scattered across the galaxy, together form an instrument of extraordinary sensitivity to the warping of spacetime. So the clock at the heart of the star, which initially made the pulsing signal seem artificial, has become one of the most valuable tools in modern astrophysics. The very regularity that puzzled Bell and Hewish, that suggested an artificial origin, turned out to be a natural phenomenon of immense scientific utility. The precise timekeeping of pulsars allows astronomers to study neutron stars, detect companions, test general relativity, and search for gravitational waves. The signal that briefly seemed to be a message from aliens became instead a precise cosmic clock, and in that role, it has contributed enormously to our understanding of the universe. What seemed like a sign of intelligence became a tool for the intelligence of those who learned to read it. There is a pleasing symmetry in this turn of events. The regularity of the pulses was, at first, the very thing that made them suspect, too perfect to be natural, too precise to be anything but designed. And yet that same regularity, once understood, became the source of the pulsar's greatest value. The feature that had nearly fooled the discoverers into thinking they had found aliens was the feature that made pulsars into the finest natural clocks in the cosmos. Nature's precision, mistaken for design, turned out to be a gift more useful than any beacon could have been. The connection between pulsars and the deaths of massive stars was confirmed dramatically by the discovery of a pulsar at the heart of the Crab Nebula, a famous remnant of a supernova explosion. This discovery provided a kind of smoking gun, directly linking pulsars to supernovae and confirming the theory that pulsars are the collapsed remnants of stars that exploded. The Crab pulsar tied the whole story together. The Crab Nebula is one of the most famous objects in astronomy. It is the remnant of a supernova, a massive star that exploded, observed and recorded by astronomers in the year 1054, nearly 1,000 years ago. The explosion was bright enough to be visible in daylight for weeks, and it was recorded by observers in several parts of the world. What remains today is an expanding cloud of gas and dust, the debris of the explosion glowing with the energy of the event. The Crab Nebula has been studied intensively as a prime example of a supernova remnant. According to the theory of neutron star formation, a supernova explosion should leave behind a neutron star, the collapsed core of the exploded star. If the theory was correct, the Crab Nebula, as the remnant of a supernova, should contain a neutron star at its center. And if pulsars are neutron stars, then this central neutron star might be detectable as a pulsar if its beams happen to sweep across the Earth. The search for a pulsar in the Crab Nebula was therefore a crucial test of the theory connecting pulsars, neutron stars, and supernovae. The search was successful. A pulsar was discovered at the center of the Crab Nebula, pulsing rapidly, about 30 times per second, much faster than the first pulsars discovered. This rapid pulsation was consistent with a young neutron star, formed relatively recently in the supernova of 1054, still spinning very fast. The discovery of the Crab pulsar confirmed in a single stroke that the Crab Nebula contained a neutron star, that this neutron star was observable as a pulsar, and that pulsars are indeed associated with supernova remnants. It was a powerful confirmation of the whole theoretical framework. The Crab pulsar provided several important confirmations. First, it directly linked a pulsar to a supernova remnant of known age, confirming that pulsars form in supernova explosions. Second, its rapid pulsation, faster than the first pulsars, confirmed that young neutron stars spin very fast, as expected from the conservation of angular momentum during collapse. Third, its location at the center of the nebula, where the collapsed core should be, matched the prediction of where a neutron star should form. All of these confirmations strengthened the theory enormously. The Crab pulsar also provided a natural laboratory for studying the slowing of pulsar rotation. Because the age of the Crab pulsar is known, it formed in the supernova of 1054, astronomers could study how its rotation had slowed over the nearly 1,000 years since its formation. The observed slowing was consistent with the theory of a rotating neutron star losing energy. Indeed, the energy lost by the slowing rotation of the Crab pulsar was found to match the energy needed to power the glowing nebula around it, providing a beautiful confirmation that the pulsar's rotational energy was driving the nebula's emission. This last point is particularly elegant. The Crab Nebula glows with energy, and astronomers had wondered what powered this glow, since the supernova explosion itself was long past. The discovery of the Crab pulsar provided the answer. The pulsar, slowing its rotation, transfers its rotational energy to the surrounding nebula, powering its glow. The energy budget matched precisely. The rotational energy lost by the pulsar equaled the energy radiated by the nebula. This confirmed not only the nature of the pulsar, but also its role in energizing its surroundings, tying together the pulsar and the nebula in a single coherent picture. The Crab Nebula and its pulsar thus provided a smoking gun for the theory of pulsars as neutron stars formed in supernova. The discovery confirmed the connection between pulsars, neutron stars, and supernova explosions, validated the prediction of rapid rotation in young neutron stars, and demonstrated the pulsar's role in powering its nebula. It was a triumph for the theory, transforming the explanation of pulsars from a plausible model into a well-confirmed understanding. The dead star at the heart of the Crab Nebula, spinning 30 times a second, was the clinching evidence that the little green men were, in fact, the corpses of exploded stars. And there was a further marvel in the timing. Humans had witnessed the very explosion that created this pulsar, recording it in their chronicles nearly 1,000 years before anyone understood what they had seen. The light of 1054 and the pulses of the 20th century were two glimpses of the same event, separated by the long centuries it took for science to catch up with the sky. The discovery of pulsars was recognized with the Nobel Prize in Physics in 1974, but the prize went to Anthony Hewish and another astronomer, Martin Ryle, not to Jocelyn Bell, who had actually made the discovery. This omission became one of the most discussed controversies in the history of the Nobel Prizes, raising questions about credit, recognition, and the treatment of junior researchers and women in science. The story of the prize is an important part of the larger story of the discovery. The 1974 Nobel Prize in Physics was awarded to Hewish, in part for his role in the discovery of pulsars, and to Ryle for his pioneering work in radio astronomy more broadly. It was the first Nobel Prize awarded for work in astronomy, marking the recognition of radio astronomy as a major field. Hewish was Bell Burnell's doctoral supervisor and the leader of the research group, and he had played an important role in the investigation of the pulsing signals. But it was Bell Burnell who had actually noticed the signal, recognized its significance, and tracked it down through careful analysis. The omission of Bell Burnell from the prize was immediately controversial. Many in the scientific community felt that she had been unfairly overlooked, that her central role in the discovery merited recognition. She had been the one to notice the bit of scruff, to recognize it as something unusual, to confirm that it recurred, and to track it down. Without her careful attention and persistence, the discovery might not have been made. To award the prize to her supervisor while omitting her struck many as an injustice, reflecting the tendency to credit senior researchers over the junior ones who do the actual work, and perhaps also reflecting the biases against women in science at the time. The controversy has been discussed extensively over the years. Some have argued that the omission reflected the hierarchical structure of science, in which the head of a research group is credited with the group's discoveries, regardless of who did the actual work. Others have pointed to the gender dynamics, suggesting that Bell Burnell, as a woman and a graduate student, was overlooked in a way that a man might not have been. Still others have noted the general difficulty of assigning credit for discoveries that involve many people, and the Nobel Committee's tendency to favour senior figures. The omission has become a case study in the politics of scientific credit. Bell Burnell's own response to the controversy has been remarkable for its grace. She has consistently declined to express bitterness about the omission, instead taking a measured and gracious view. She has argued that Nobel Prizes should generally go to senior researchers rather than students, except in exceptional cases, and has said that she does not believe her case was exceptional enough to warrant the prize. She has also pointed out, with humour, that she is in good company among those overlooked by the Nobel Committee. Her dignified response has only enhanced her reputation, earning her widespread admiration. Whatever the reasons for the omission, Bell Burnell's contribution to the discovery has been widely recognised in other ways. She has received numerous honours and awards over the course of her distinguished career. She has held prestigious positions, been elected to learned societies, and been honoured as a dame. Her role in the discovery of pulsars is now widely acknowledged, and she is celebrated as one of the most important astronomers of her generation. The Nobel omission, while a genuine injustice in the eyes of many, did not prevent her from achieving recognition and a distinguished career. In a striking coda to the story, Bell Burnell was awarded a major scientific prize in 2018, the Breakthrough Prize in Fundamental Physics, carrying a substantial monetary award. In a gesture that reflected her character, she donated the entire sum, several $1 million, to fund scholarships for students from underrepresented groups in physics, including women, ethnic minorities, and refugees. This act transformed the belated recognition into a means of helping others, addressing the very kinds of barriers that she herself had faced. It was a fitting and generous response to a career marked by both achievement and the experience of being overlooked. The story of the Nobel Prize and who was left out is thus a complex and revealing part of the Pulsar discovery. It highlights the difficulties of assigning credit in science, the biases that can affect recognition, and the particular challenges faced by women and junior researchers. But it also showcases the grace and generosity of Bell Burnell herself, who responded to an injustice with dignity and turned a later recognition into an opportunity to help others. The discovery of pulsars was a scientific triumph, but the story of its recognition is a human one, with lessons about fairness, credit, and character that extend beyond the science itself. Jocelyn Bell Burnell's response to the events surrounding the discovery, the omission from the Nobel Prize, the challenges of being a woman in science, the complexities of credit and recognition, reveals a great deal about her character and offers lessons that go beyond the specifics of her case. Her grace, resilience, and generosity in the face of difficulty have made her an admired figure, a role model for the scientists and others alike. When the Nobel Prize was awarded to her supervisor in 1974, omitting her, Bell Burnell had every reason to feel aggrieved. She had made the discovery, and the recognition had gone to someone else. Many in her position would have expressed bitterness or resentment. But Bell Burnell chose a different path. She declined to be bitter, instead taking a measured view of the situation. She argued that the structure of science, in which credit often goes to senior researchers, was not unreasonable, and that her case was not exceptional enough to warrant an exception. Whether or not one agrees with this assessment, her gracious acceptance of it was remarkable. This grace was not weakness or passivity. Bell Burnell was clear-eyed about the situation and did not pretend that everything was fair. She acknowledged the difficulties she had faced, including the discrimination and harassment she had experienced as a woman in science, but she chose to respond to these difficulties with resilience rather than resentment, focusing on her work and her contributions rather than dwelling on the injustices. This combination of clear-eyed honesty about the problems and a constructive, non-bitter response is characteristic of her approach. Throughout her career, Bell Burnell faced the challenges common to women in science during her era. She was often the only woman in her classes or workplaces, subject to discrimination and to the assumption that she did not belong. She had to balance her career with family responsibilities, at a time when this was especially difficult for women in science. She worked part-time for periods and faced the obstacles that part-time and interrupted careers posed for advancement. Despite these challenges, she persevered, building a distinguished career and rising to prominence in her field. Bell Burnell has been an advocate for women and other underrepresented groups in science. Drawing on her own experiences, she has worked to improve the situation for those who face the kinds of barriers she encountered. Her donation of the Breakthrough Prize money, To fund scholarships for underrepresented students was a concrete expression of this commitment. She has also spoken and written about the challenges faced by women in science and the importance of diversity in the field. Her advocacy has made her a significant figure not only as a scientist but as a champion of fairness and inclusion in science. Her response to the discovery and its aftermath also reflects a particular attitude towards science itself. Bell Burnell has emphasized the collaborative nature of the work, the importance of careful attention and persistence, and the role of luck and circumstance in discovery. She has been generous in acknowledging the contributions of others and modest about her own role, even as she has rightly claimed her place in the history of the discovery. This balanced, generous attitude towards science and credit is part of what makes her an admired figure. There is a lesson in Bell Burnell's response that extends beyond science. Faced with injustice and difficulty, she responded with grace, resilience, and generosity, neither denying the problems nor being consumed by them. She focused on her work, advocated for others, and turned later recognition into an opportunity to help those facing similar barriers. This is a model of how to respond to adversity with dignity and constructiveness, a model that resonates well beyond the specific context of her scientific career. Jocelyn Bell Burnell's response to the discovery and its aftermath is, in the end, an integral part of the story. The discovery of pulsars was a great scientific achievement, but the way Bell Burnell handled the complexities that followed, the omission, the challenges, the belated recognition, reveals a character of unusual grace and strength. She has become admired not only for making one of the great discoveries of the 20th century, but for the dignity and generosity with which she has carried that legacy. Her story is one of scientific triumph and personal character intertwined, and both deserve to be remembered. There is a particular kind of strength in responding to unfairness without being diminished by it. Bell Burnell could have spent her career as a symbol of grievance, defined by the prize she did not receive. Instead, she defined herself by what she did, the discovery she made, the students she championed, the example she set. The Nobel omission, which might have embittered a lesser person, became in her hands almost an afterthought, a footnote to a life of substance. She refused to let an injustice define her, and in that refusal she found a freedom that the prize itself could never have given. It is a lesson that reaches far beyond astronomy, that we are shaped not only by what happens to us, but by how we choose to carry it. In the decades since their discovery, pulsars have proven to be extraordinarily valuable tools for physics and astronomy. Far from being mere curiosities, they have become instruments for probing some of the deepest questions in science, from the nature of matter to the structure of space-time. The transformation of pulsars from puzzling signals into precision scientific instruments is one of the great success stories of modern astrophysics. The key to the scientific value of pulsars is their precise timekeeping. As discussed, the regular pulses of a pulsar function as a clock of extraordinary precision, particularly in the case of millisecond pulsars. This precision allows astronomers to make measurements of exquisite sensitivity, detecting tiny effects through their influence on the timing of the pulses. The pulsar clock is the foundation of most applications of pulsars in physics, enabling a wide range of precise measurements that would otherwise be impossible. Pulsars serve as natural laboratories for studying matter under extreme conditions. The matter in a neutron star is compressed to densities beyond anything achievable on Earth, in a state that cannot be produced or studied in any laboratory. By studying pulsars, their masses, their sizes, their behavior, astronomers can probe the physics of this extreme matter, testing theories of how matter behaves at nuclear densities and beyond. Pulsars thus provide access to a regime of physics that is otherwise inaccessible, allowing scientists to test their theories of dense matter against real objects. Pulsars also allow precise measurements of neutron star masses, which constrain the physics of dense matter. In binary systems, where a pulsar orbits a companion, the timing of the pulses reveals the orbital motion, from which the masses of the objects can be determined. These mass measurements are important because the maximum possible mass of a neutron star depends on the behavior of matter at extreme densities, which is not fully understood. By measuring neutron star masses precisely, astronomers can test theories of dense matter and constrain the properties of the exotic material in neutron star interiors. Beyond the study of matter, pulsars are powerful tools for testing theories of gravity. In binary systems containing pulsars, especially those with two neutron stars, the precise timing of the pulses allows astronomers to measure relativistic effects predicted by Einstein's general relativity. These effects include the precession of the orbit, the slowing of time in strong gravitational fields, and the loss of energy to gravitational waves. The measurements provide stringent tests of general relativity in the strong field regime, where gravity is intense, a regime far beyond what can be tested in the solar system. So far, general relativity has passed all these tests with flying colours. Pulsars have also been used as tools for studying the interstellar medium, the gas and dust between the stars. As pulsar signals travel through this medium, they are affected in measurable ways, with different frequencies arriving at slightly different times due to their interaction with the intervening material. By measuring these effects, astronomers can probe the properties of the interstellar medium along the line of sight to the pulsar, mapping the distribution of material in the galaxy. The pulsar signals thus carry information not only about the pulsar itself, but about the space through which they have travelled. The applications of pulsars continue to expand as the techniques for studying them improve. New pulsars are discovered regularly, including exotic systems that provide new opportunities for testing physics. Arrays of pulsars are being used to search for gravitational waves. Millisecond pulsars are being studied as potential tools for navigation and timekeeping. The field of pulsar science remains vibrant and productive, more than half a century after the initial discovery. What began as a puzzling signal has grown into a rich field of research, with pulsars serving as versatile tools for exploring the universe. The transformation of pulsars into scientific tools is a testament to the value of basic research and unexpected discovery. No one set out to discover pulsars. They appeared unexpectedly in data gathered for another purpose, and no one could have predicted, at the time of the discovery, how valuable these objects would become as tools for physics. The pulsing signals that briefly suggested aliens, and then revealed a new kind of star, have become instruments for probing the deepest questions in science. This is how science often advances, through unexpected discoveries that open up new possibilities, leading in directions no one anticipated. The little green men turned out to be not a message, but a gift, a new class of precision instruments, scattered throughout the galaxy, waiting to be used. It is a pattern worth remembering whenever the value of curiosity-driven research is questioned. The most useful tools are often the ones no one knew they needed until they were found. Among the most remarkable applications of pulsars is their use in testing Einstein's general theory of relativity, our best theory of gravity. Pulsars, particularly those in binary systems, provide tests of general relativity in conditions far more extreme than anything available in the solar system. And these tests have confirmed Einstein's theory to extraordinary precision. The use of dead stars to probe the nature of gravity is one of the most elegant achievements of modern physics. General relativity, formulated by Einstein in 1915, describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. The theory makes a number of predictions that differ from the older Newtonian theory of gravity, particularly in strong gravitational fields. In the prohibitively weak gravity of the solar system, these differences are tiny, and testing them requires great precision. To test general relativity in strong gravitational fields, where its predictions differ more dramatically from Newtonian gravity, requires extreme conditions found near neutron stars. Binary pulsars, systems in which a pulsar orbits a companion, often another neutron star, provide ideal laboratories for testing general relativity. In these systems, the strong gravitational fields and rapid orbital motion produce relativistic effects that are large enough to measure, and the precise timing of the pulsar's pulses allows these effects to be measured with great accuracy. The pulsar serves as a precise clock, and the variations in the timing of its pulses reveal the relativistic effects in the orbit. This combination of strong gravity and precise timing makes binary pulsars powerful tools for testing the theory. One of the most famous tests came from a binary pulsar discovered in the 1970s, a system of two neutron stars orbiting each other, one of them a pulsar. General relativity predicts that such a system should lose energy by emitting gravitational waves, ripples in spacetime produced by the accelerating masses. As the system loses energy, the two stars should spiral gradually closer together, and the orbital period should decrease. By precisely timing the pulsar over many years, astronomers measured the change in the orbital period and found that it matched the prediction of general relativity remarkably well. This was the first observational evidence for gravitational waves, albeit indirect, and it provided a stringent test of the theory. This measurement was so significant that it was recognized with a Nobel Prize. It confirmed a key prediction of general relativity, the existence of gravitational waves decades before such waves were detected directly. The binary pulsar's orbit was decaying at exactly the rate predicted by the theory, as the system radiated away energy in gravitational waves. The agreement between prediction and observation was a triumph for general relativity, and a demonstration of the power of pulsars as tools for testing fundamental physics. Other relativistic effects have also been measured in binary pulsars. These include the precession of the orbit, a gradual rotation of the orbital ellipse, analogous to the precession of Mercury's orbit that provided an early test of general relativity, but much larger in the strong gravity of a binary pulsar. They also include the slowing of time in the strong gravitational field, and the bending and delay of the pulsar signals as they pass through the companion's gravitational field. Each of these effects can be measured through precise pulsar timing, and each provides a test of general relativity. The theory has passed all these tests, confirming its predictions in the strong field regime. The precision of these tests is remarkable. In some binary pulsar systems, general relativity has been confirmed to a precision of a fraction of a percent, making these among the most stringent tests of the theory ever performed. The agreement between the theory's predictions and the observations is a powerful confirmation that general relativity correctly describes gravity, even in the extreme conditions near neutron stars. Pulsars have thus become one of the most important tools for testing our understanding of gravity, probing regimes far beyond the reach of laboratory experiments or solar system observations. There is a beautiful irony in using dead stars to test our theories of gravity. Neutron stars are the corpses of stars that have exhausted their fuel and collapsed, the endpoints of stellar evolution. Yet these dead stars, through their precise pulses and strong gravity, have become our most powerful tools for probing the living theory of gravity that governs the cosmos. The signal that briefly seemed to come from aliens has become a means of testing Einstein, confirming our deepest understanding of space, time, and gravity. The little green men, it turns out, had something to teach us after all. Not about alien civilizations, but about the fundamental nature of the universe itself and the curvature of the space-time through which we all move. One of the more unexpected and practical applications of pulsars is their potential use for navigation. Because pulsars are precise, stable clocks distributed throughout the galaxy, they could in principle be used to determine position and time in space, much as the satellites of the Global Positioning System are used for navigation on Earth. This concept, sometimes called pulsar navigation, represents a fascinating practical application of these exotic objects. Navigation, fundamentally, requires knowing where you are. On Earth, modern navigation relies on signals from satellites, which broadcast precise timing signals that a receiver can use to determine its position. By measuring the time it takes for signals from several satellites to arrive, a receiver can calculate its distance from each satellite and thereby determine its location. This system works well near the Earth, where the satellites are located, but it does not extend to deep space, far from the Earth and its satellites. For navigation in deep space, a different reference is needed. Pulsars could provide that reference. Because pulsars are distributed throughout the galaxy and emit precise, regular pulses, they could serve as natural beacons for navigation in deep space. A spacecraft equipped with a detector could observe several pulsars, measure the timing of their pulses, and use this information to determine its position and time. The principle is similar to satellite navigation, but using natural cosmic clocks instead of artificial satellites, and working throughout the galaxy rather than just near the Earth. The pulsars provide a galaxy-wide reference frame for navigation. The key to pulsar navigation is the precise and predictable timing of the pulses. Because the pulses arrive at regular, well-characterized intervals, a spacecraft can use them as timing references. By comparing the observed arrival times of pulses from several pulsars with the predicted arrival times at a reference location, the spacecraft can determine its position relative to that reference. The more pulses observed and the more precise the timing, the more accurate the position determination. Millisecond pulses with their extremely precise timing would be especially valuable for this purpose. The concept of pulsar navigation has been studied and even tested experimentally. Experiments have been conducted to demonstrate the feasibility of using pulsar signals for navigation, including tests aboard spacecraft. These experiments have shown that pulsar navigation is technically possible, though it faces practical challenges, including the need for sensitive detectors and the relatively weak signals from pulsars. As the technology develops, pulsar navigation could become a practical tool for deep space missions, providing an autonomous means of navigation that does not depend on signals from Earth. Pulsar navigation has an appealing elegance. It would allow spacecraft to navigate using natural objects, independent of any infrastructure built by humans. A spacecraft far from Earth, beyond the reach of terrestrial navigation systems, could orient itself using the cosmic clock scattered throughout the galaxy. This autonomy would be valuable for deep space missions, which cannot rely on constant communication with Earth. The pulsars in this application become cosmic lighthouses in a more literal sense, beacons that guide travelers through the depths of space. There is also a poetic dimension to the idea, connected to humanity's long history of navigating by the stars. For millennia, sailors and travelers navigated by the positions of the stars, using the fixed patterns of the heavens to find their way. Pulsar navigation is a modern, sophisticated version of this ancient practice, using not the visible positions of stars, but the precise timing of pulsar signals. It connects the cutting edge of astrophysics to the age-old human endeavour of finding one's way by the heavens. The dead stars, through their regular pulses, could guide future travellers across the galaxy, as the visible stars guided travellers across the oceans of Earth. Indeed, pulsars have already been used in a symbolic act of cosmic navigation. A famous diagram included on spacecraft launched from Earth shows the position of the Sun relative to a set of pulsars, identified by their periods. The idea was that any intelligent beings who might find the spacecraft could use this pulsar map to locate the Sun, and thereby the origin of the spacecraft. In this sense, pulsars have already been used as cosmic reference points, marking the location of humanity for any aliens who might one day encounter our spacecraft. The objects that briefly seemed to be alien beacons have become, in this symbolic act, beacons by which we mark our own location for possible aliens, a fitting turn in the story. There is a deep poetry in this reversal. The pulsars were once suspected of being signals sent by aliens to us. Now we have used them in effect to send a signal of our own, a map drawn in the language of pulsar periods, pointing back to the small blue world where the whole story began. If those spacecraft are ever found, and the map ever read, the finders will trace a set of lines back to a single star, guided by the very objects that once made us wonder whether we were alone. The little green men who never existed may yet help real beings find us. The episode of the Little Green Men holds important lessons for the ongoing search for extraterrestrial intelligence, the scientific effort to detect signals from alien civilizations. The pulsar discovery showed both how a natural phenomenon could mimic an artificial signal and how careful science could distinguish between the two. These lessons continue to inform the search for genuine alien signals today. The search for extraterrestrial intelligence, often abbreviated as SETI, looks for signals that would indicate the presence of an alien civilization. The basic idea is to search for radio signals, or other signs, that have the characteristics of artificial transmissions, features that would distinguish them from natural sources. As discussed earlier, regularity, narrow frequency bands, and other patterns suggestive of design are among the features that searchers look for. The Pulsar episode showed that such features, while suggestive, do not by themselves prove an artificial origin, since natural sources can also produce them. The Pulsar discovery was, in a sense, a dry run for SETI. The team detected a signal with artificial seeming characteristics, considered the possibility of an alien origin, and then determined, through careful investigation, that the signal was natural. This is exactly the process that a genuine SETI detection would have to go through. Detect a candidate signal, consider the possibility that it is artificial, and then rigorously test whether it could be natural before concluding that it is artificial. The Pulsar episode demonstrated the importance of this process and the danger of jumping to conclusions. One key lesson is the importance of ruling out natural explanations. The Pulsar signal seemed artificial, but it turned out to be natural, a new kind of natural object that no one had anticipated. This shows that natural phenomena can be more varied and surprising than expected, capable of producing signals that seem artificial. Before concluding that a signal is from aliens, searchers must rule out not only known natural sources, but also the possibility of unknown natural phenomena. The universe is full of surprises, and an artificial seeming signal might be a natural phenomenon we have not yet understood. Another lesson is the importance of multiple instances and distribution. The discovery of a second pulsing source in a different part of the sky was decisive in ruling out the alien hypothesis, because a widespread phenomenon is more likely natural than artificial. For SETI, this suggests that a genuine alien signal might be distinguished by its uniqueness or localization, a signal from a single specific source rather than a widespread phenomenon. The distribution of a signal is evidence about its origin, and searchers must consider whether a candidate signal is unique or part of a broader natural pattern. The Pulsar episode also illustrates the value of careful, skeptical investigation. The team did not announce an alien detection prematurely. They investigated carefully, ruled out alternatives, and ultimately found the natural explanation. This skeptical, thorough approach is essential for SETI, where the temptation to announce a momentous discovery must be balanced against the need for certainty. A premature or mistaken announcement of an alien signal would be damaging, and the Pulsar episode shows the importance of careful verification before any such claim. At the same time, the episode shows that taking the artificial possibility seriously is not foolish. The team did consider the possibility of an alien origin because the signal's features genuinely suggested it. This was reasonable, given the characteristics of the signal. The lesson is not that one should never consider artificial origins, but that one should consider them as one hypothesis among others, to be tested rigorously rather than accepted prematurely. The artificial possibility deserves serious consideration, but it must be subjected to the same scrutiny as any other hypothesis. The search for genuine alien signals continues today using sophisticated instruments and techniques. Searchers look for signals with artificial characteristics while remaining mindful of the lessons of the Pulsar episode, that natural phenomena can mimic artificial signals, that distribution and uniqueness matter, and that careful verification is essential. The discovery of pulsars, though it turned out not to be a detection of aliens, helped to refine the methods and the thinking of the search for extraterrestrial intelligence. It was a valuable lesson in how to search for signals that are real and how to avoid being fooled by the unexpected richness of nature. Whether a genuine alien signal will ever be detected remains unknown, but if one is, the process of confirming it will owe something to the lessons learned in 1967, when a graduate student detected a signal that seemed artificial, and careful science revealed it to be the beam of a spinning dead star. The search for the real signal goes on, informed by the memory of the little green men who turned out to be neutron stars. The Pulsar episode raises a deep question that goes to the heart of the search for extraterrestrial intelligence, and more broadly, to how we interpret the signals we receive from the universe. What counts as a message? What distinguishes a genuine communication from a natural phenomenon? This question, which the Pulsar discovery brought into sharp focus, turns out to be subtler than it might first appear. At first glance, the distinction seems clear. A message is something produced by an intelligence, intended to convey information. A natural phenomenon is something produced by physical processes, without intention or meaning. A radio broadcast is a message. The radio noise from a planet is a natural phenomenon. But the Pulsar episode showed that this distinction can be hard to draw in practice. The Pulsar signal had features that suggested intelligence, regularity, precision, yet it was produced by a natural process, without any intention or meaning. The features we associate with messages can be produced by nature. This raises the question of what features genuinely distinguish a message from a natural signal. Regularity, as we have seen, is not sufficient. Nature can produce regular signals. Narrow frequency bands are not sufficient. Some natural processes are narrowband. What then would genuinely indicate an artificial origin? One answer is complexity of a particular kind, the kind of complexity that carries information, that conveys meaning. A message, presumably, would not just be regular, it would be patterned in a way that encodes content, that says something. A purely regular signal like a pulsar's carries no content. It is the same pulse over and over. But even this is subtle. How do we recognize information-bearing complexity? A signal might be complex without carrying a message, or might carry a message in a form we do not recognize. The challenge of distinguishing meaningful signals from meaningless ones, and of recognizing meaning in unfamiliar forms, is genuinely difficult. We have intuitions about what messages look like, based on human communication, but an alien message might not conform to those intuitions. It might use forms of encoding we do not anticipate, or convey meaning in ways we cannot easily recognize. There is also the question of intention. A message, we usually think, is produced with the intention to communicate. But intention is hard to detect from a signal alone. We infer intention from the characteristics of a signal, but those characteristics, as the Pulsar showed, can be produced without intention. A signal might seem intentional but be natural, or it might be genuinely intentional but seem natural. The link between the characteristics of a signal and the intention behind it is not straightforward. We cannot directly perceive intention. We can only infer it from the signal, and that inference can be mistaken. The Pulsar episode suggests a kind of humility about our ability to recognize messages. We thought briefly that we might have detected a message based on the signal's characteristics. We were wrong, the signal was natural. This shows that our intuitions about what counts as a message can mislead us. Nature can mimic the features we associate with intelligence, and we may not be able to tell the difference from the signal alone. Recognizing a genuine message, if we ever receive one, may be harder than we think, requiring us to distinguish it not only from known natural phenomena, but from unknown ones that might mimic intelligence. This has implications for how we should approach the search for extraterrestrial intelligence. We should be cautious about concluding that a signal is a message, recognizing that natural phenomena can mimic artificial ones. We should look for features that genuinely indicate intelligence, while acknowledging the difficulty of identifying such features with confidence. And we should be prepared for the possibility that a genuine message might not look the way we expect, or that an apparent message might turn out to be natural. The question of what counts as a message is central to the search, and the Pulsar episode shows that it does not have an easy answer. In a deeper sense, the question of what counts as a message touches on the nature of meaning itself. Meaning, it seems, is not simply a property of a signal, it depends on the relationship between the signal, its source, and its interpreter. A pulsar's pulses carry no meaning even though they are regular because there is no intention behind them and no content encoded in them. A genuine message carries meaning because it is produced with intention and encodes content. But detecting meaning, distinguishing the meaningful from the meaningless, is a profound challenge, one that the search for extraterrestrial intelligence must grapple with, and one that the Pulsar episode brought into sharp and instructive focus. What counts as a message remains, in the end, a question without a simple answer. The story of the little green men, the brief period when a pulsar was thought to be a possible alien signal, holds lessons that extend far beyond the specific discovery. It is a story about how science meets the unknown, about the interplay of expectation and observation, about the surprising richness of nature, and about the human dimension of scientific discovery. As we close, it is worth reflecting on what this remarkable episode teaches us. The first lesson is about the richness and surprise of nature. The pulsar signal seemed artificial because nothing in the known catalogue of natural objects could produce such regular, precise pulses, but the explanation turned out to be a natural object more exotic than anyone had imagined. A city-sunned ball of neutron matter, spinning rapidly, beaming radiation across space. Nature, it turned out, was stranger than the alien hypothesis had supposed. This is a recurring theme in the history of science. The universe is more surprising, more various, more wonderful than our expectations. When we encounter something we cannot explain, the explanation may be a natural phenomenon stranger than anything we'd conceived. The second lesson is about the importance of careful observation and honest investigation. The discovery was made because a graduate student paid close attention to her data, noticed an anomaly, and pursued it with diligence and curiosity. The interpretation was correct because the team investigated carefully, ruled out alternatives, and followed the evidence where it led, rather than jumping to conclusions. This careful, honest approach, taking the data seriously, considering the possibilities, testing them rigorously, is the heart of good science. The discovery of pulsars is a model of how science should be done. The third lesson concerns the proper handling of extraordinary possibilities. The team considered the possibility of an alien signal because the evidence genuinely suggested it, but they did not accept it prematurely. They held it as one hypothesis among others, to be tested, and they were prepared to abandon it when the evidence pointed elsewhere. This balance, taking extraordinary possibilities seriously, without accepting them prematurely, is essential to science. It allows for genuine discovery while guarding against error. The team neither dismissed the alien possibility out of hand, nor embraced it without sufficient evidence. The fourth lesson is about the human dimension of science. The story of the pulsar discovery is not just about signals and neutron stars, it is about people, about Jocelyn Bell-Bonnell's attention and persistence, about the team's investigation, about the controversy over credit, about Bell-Bonnell's gracious response to being overlooked. Science is a human endeavour, shaped by the character, the choices, and the circumstances of the people who do it. The discovery of pulsars reminds us that behind every scientific achievement are human beings, with their virtues and their struggles, their triumphs and their disappointments. There is also a lesson about expectations and humility. Astronomers thought the sky was largely mapped, the major categories of objects known. The discovery of pulsars showed that this confidence was misplaced, that the universe held categories of objects no one had anticipated. This is a reminder to hold our knowledge humbly, to remain open to surprise, to recognize that our current understanding is incomplete. The universe has more to teach us than we know, and the next great discovery may overturn our expectations as thoroughly as pulsars did. The episode also illuminates the search for extraterrestrial intelligence, a search that continues today. The little green men turned out to be neutron stars, but the question they raised, are we alone, remains open. Whether we will ever detect a genuine signal from another civilization remains unknown. But the search continues, animated by the same curiosity that led Belle Burnell to pursue her bit of scruff. When you consider it, there is something fitting in the way the story turned out. The signal that seemed to be a message from another mind was, in fact, a message of a different kind, a message from nature, revealing one of its most extraordinary secrets. The universe did not announce the presence of aliens. It announced the existence of neutron stars, objects of such extremity that they had been only theoretical until that moment. In seeking to understand a possible message from the stars, astronomers learned something profound about the stars themselves. The little green men gave way to something stranger and, in its way, more wonderful, the spinning corpses of dead stars keeping time in the dark. And perhaps that's the deepest lesson of all. When we reach out to the universe hoping to find others like ourselves, we may instead find the universe itself in all its strange and unexpected richness. The search for meaning among the stars leads us again and again to discoveries we did not anticipate, to a cosmos more various and more wonderful than our theories had supposed. The little green men were not there, but in looking we found the lighthouses of the dead, sweeping their beams across the galaxy, and we understood a little better the universe in which we find ourselves. That perhaps is enough for tonight.